Test, test. 1, 2, 3. A,
Okay.
B,
relatively short talk slots, so that gives us a lot of opportunity to interaction and coming up with new ideas, doing stuff together. I hope this will be a very productive conference in that sense. It is my particular pleasure now to introduce our keynote speaker, Amir Sheikha.
Sheikha? Yeah, that's fine.
He's currently a reader, as the British say, or for the rest of the world, an associate professor at Edinburgh University. He did his PhD in 2018 at EPFL.
Yeah.
Was already about data structures. So he seems to be a little bit kind of married to this, which I think is great. In particular at times where everybody is hyping just for the next grant. It is very nice to see some people stick to a certain core area. He then went to Edinburgh, I believe.
First to Oxford and then Edinburgh.
And then I thought it was Edinburgh, but
no, Oxford, then Edinburgh.
So he knows it obviously much better than I do. So now he's in Edinburgh and he's going to talk to us about his ontologies, I think, for data structures.
Yeah. Thank you so much, Bodo, for the introduction. This is Amir Sheikha. You can call me Amir. And today I'm presenting a series of line of work on basically democratizing data science by leveraging structure, or basically the title that I chose for here to make it more array-like is actually array and data processing by leveraging structure. And this is a joint work with a bunch of collaborators that you can see here. Many of them are actually very well-established researchers. Most of them are on the left side, actually, yeah, your left side. And the right ones are mostly my students. So let's first start with the motivation. So we are living in an era where we are surrounded by a lot of data. So on this slide, you can see that in every single minute, how much data is being produced throughout the web. And so in order to, just data for the sake of data is going to be useless. We have to process it in order to extract some insights from it. We have different kinds of processing that we can do. And perhaps this workshop mostly is concerned with the data of this kind, which is basically matrices or tensors, which are very dense. However, we could have also data of this kind where many of the elements are actually zero. There is only a small portion of the data that is going to be non-zero. So for the left one, we are going to use, of course, arrays to represent them. And in this talk, I'm going to show for various types of data that are of the right form, how we are going to present them. And okay, so here I'm using a bit of nonlinear narrative. So I'm going to spoil what are we going to use in order to present it, which is basically a dictionary. So perhaps my talk would form better to a dictionary workshop, but yeah, I'm going to fit it to the array workshop. So this is the outline of my talk. So the x-axis is the time. The y-axis is the depth of the technical depth. So at the beginning, I'm going to first talk about the end-to-end data science workloads. Then I'm going to go over sparse tensor algebra, then a bit on sparse differentiation, then a bit deeper into structured tensor algebra, and then I'm going to say briefly sum up and tell you a bit the future line of work that we can do. So let's start with the end-to-end data science. So I said that we are surrounded by data, we need to process them. So what are we using to write programs that are processing the data? Programming languages. So which programming languages data scientists are mostly using? Python. Yes, that's the sad reality that programming language researchers invest a lot of time on developing this fancy programming language with static types and all these kind of things. And at the end of the day, people are using Python. But a bit of good news that maybe doesn't make programming language people that happy, but database people very happy, is that the second language is actually SQL. And what is the reason behind that? So if you take a look at the end-to-end data science pipeline, you can see that at the beginning, we have the data in unstructured form or semi-structured form in the form of a graph or relational data. We do some sort of data pre-processing, data wrangling. For that, we are going to use either SQL or Python libraries. We convert it to tabular data. Then we are going to prepare the data further. And in order to feed it into some statistical tools or machine learning libraries, we have to convert it into the tensor format. And then we feed it to R or Python, one of these libraries, in order to make sense of the data. So what is the issue with this pipeline? You can see that there are many different environments that are involved here. So you have to do part of it in Python, part of it in R, part of it in SQL. And if you see in the undergraduate course in databases, there have been so much theory on third normal form, how to normalize the data in order to give better structure to it, reduce redundancy. And yeah, maybe the relational data that we had at the beginning, it has so much structure inside it. But as we go through this pipeline, that structure is going to be thrown away. So we can no longer leverage that structure towards the end of the pipeline. At the end of the pipeline, it's a tensor. We have no idea where the elements in the tensor are redundant in order to perhaps do a better job, a faster job. So to classify the types of workloads that these different components are dealing with, we can basically classify them into two general types of workloads. So one is what I call the database workload, and the other one is what we call the linear algebra workload. So for example, in the database workload, we have this online analytical processing in data warehouses, where you basically do group by, aggregates, joins, and these kind of things. In the linear algebra types of workloads, we do machine learning, computer vision, or even graph processing. We can cast it as a linear algebra problem, for example, in GraphBlast, or we do scientific computation. And the issue here is that, yeah, there are these two completely disjoint communities that are not talking that well to each other. There is some effort. So for example, there is a workshop called DBPL, which is usually co-organized together with one of these either database conferences or programming language conferences, but usually there is not that much communication across these two communities. And for example, on the programming language level or on the level of the abstractions, notations that people use in the database workload, either they're using relational algebra, or whenever they're dealing with nested data like JSON type of data, they deal with nested relational algebra. On the linear algebra workload, they either deal with linear algebra or tensor algebra. And in terms of the frameworks, so relational database systems is the usual type of the workloads that they're using, or the poor person's version of relational algebra, relational databases, which is, for example, a framework like Panda data frame in Python. And on the linear algebra side, we have TensorFlow, PyTorch, and SciPy. So, and there is not that much communication happening across these two communities. So let's see whether there is any opportunity that we can leverage in order to marry these two communities. So let's take a very high level, very, very high level view of what's happening inside a relational database system. So a relational database system, you can think of it as a compiler. We have an SQL query. There is a parser. There is like analyzer and all these kind of things that basically converts the SQL query into relational algebra. And at the end, we have an engine that takes that relational algebra expression together with the data and it's producing the answer. And a lot of magic happens inside this engine. So what is relational algebra? As the name suggests, it's an algebra for relations. And it has a bunch of constructs. So for example, selection, projection, and join, or as well as the aggregation and group by operators. So what is the nice thing with this algebra is that it's based on mathematics and logic. And because of that, we have a lot of optimization opportunities. So here you can see a bunch of algebraic identities over these operators. So for example, whenever you have a chain of selections, we can commute them with each other. Or we can basically push selections past join. So here you can see basically that the expression that is responsible for pushing selections before the join. And in practice, what it enables is a very sophisticated form of loop invariant code motion. How about machine learning frameworks or linear algebra frameworks? We have a similar picture. We have, as input, a program that is written in terms of one of these languages like Python. And we have a library that the API, we write the program using the API provided by this library. And the library behind the scenes is basically expressing all these computations in terms of linear algebra. And then there's a linear algebra framework behind the scenes that digests that linear algebra expression together with the input matrix, and it produces the answer for us. A very similar picture to the relational database system. And again, it uses linear algebra. We have a bunch of linear algebra identities that if we have a if the behind the scenes, the linear algebra framework, it has implemented some of these rules, it can basically simplify the program. The first question we are going to answer is that can we have a unified framework that basically does the optimization, unifies the optimizations that we have seen? Or even better, can do some cross-optimization across these components? And of course, the answer that we are going to say is yes, we can do that. Let me give you a you have a question?
I was going to think of an application which would require them to coexist.
Yes. So basically, whenever in the end-to-end data science pipeline that you have seen, so you have the machine learning frameworks at the end, and you have your input as a relation. So you want to do some linear algebra computation, for example, over the join of these relations. So you want to simplify globally the program that you have that has both of them together. Exactly, exactly. Yeah, whenever you have, especially in the form of graph, whenever you have a graph, it looks more and more similar to relations. So let's see one particular opportunity that we can see here. So this is a relational algebra, an extension of linear algebra expression, where it joins three relations. And on the join of these relations, it computes a group by count. So these are two join operations, and there is a group by count operator. So we can have a better version of this program by instead of first joining these relations and then doing group by aggregate, we can basically compute some partial aggregations in order to reduce the size of the intermediate results that we have. So basically, what this program is doing is that first it joins R1 and R2, and it computes a partial aggregate, and then it joins that partial aggregate with the other relation, and it again computes the further aggregations. So this is going to be significantly faster. So let's see from the linear algebra work, do we have a similar thing? That's basically whenever you're multiplying three matrices. So rather than having like a 5-level nested loop to do the multiplication of the three matrices together, we can basically first multiply two of the matrices and then multiply the result matrix with the other one. So on the database world, this is known as the pushing aggregate past join optimization. And on the linear algebra board, this is basically the matrix chain ordering. And one other interesting thing is that the choice of whether we should first do the multiplication of the first two matrices, then followed by the third matrix or not. This is also something that, for example, we use dynamic programming in linear algebra. And coincidentally, in the database world also, they are using dynamic programming in the query optimizer to decide about which join to perform first. So what I'm going to show you is a new intermediate language, which we call it STQL, that marries these two communities and can express both workloads in the same framework. So STQL stands for Semi-Ring Dictionary Query Language. So there is the dictionary term there. So let's decipher each of these words. First, what is a semi-ring? A semi-ring is basically the generalization of the idea of addition and multiplication. So we have a set of elements, R, and two binary operators, addition and multiplication, with two particular elements from that set, which we call 0 and 1, where we have a bunch of nice algebraic identities over them. So all of them are very intuitive. So for example, whenever we add an element with 0, it's going to be that element. Or whenever we multiply an element with 1, it's going to be again that element. Or if we multiply an element by 0, it's going to be 0. One interesting law is the distributivity law that connects the multiplication and addition together. So what are examples of semi-ring? A very intuitive example is the set of real numbers and natural numbers, where basically addition and multiplication, as well as 0 and 1, are the corresponding operations and identity elements. Another interesting one is the Boolean semi-ring, where we have a set of false and true, and false is the identity element of disjunction, and true is the identity element of conjunction. And we have even more interesting semi-rings. So for example, we have the so-called tropical semi-ring, which at the beginning it looks very counterintuitive. Instead of multiplication, we have the addition operator. And instead of the addition, we have min or max operator. And the identity element of the min and max operator becomes either plus infinity or minus infinity. Yeah? So believe me, whenever you do the calculation on your on paper, you will realize that actually the distributivity law applies also to minimum and plus. So we have deciphered what semi-ring meant. The next keyword was a dictionary. What is a dictionary? So the dictionary, we know what it is. So it's a collection of key-value pairs. And what is a semi-ring dictionary? It's basically one collection to rule them all the other collections that in data processing is very important. So we are using this slogan, so we have to connect it to rings. So it's basically a dictionary from keys to values, where the values are forming, not quite a ring, a semi-ring. So what can we represent with that? We can use it to represent relations in databases. So in relations in databases, in the undergraduate course for database design, basically you would see with the set algebra, whenever the relations are basically, each relation is a set of elements. So there is no duplicate. So you can represent a set of elements of type T as a dictionary from T to a Boolean value, where the Boolean value specifies whether that element is in the set or not. Or in practical databases, actually, you can have a bag of elements, meaning that an element can be inside a relation more than once. So we could have duplicates. To represent a multi-set or a bag, we can basically represent it again as a dictionary from that element to its multiplicity. How many times do we see that in that collection? And also, we can represent a vector with a dictionary. A vector is going to be basically a dictionary from the index to the value that is located in that index. And a matrix is a dictionary from the pair of indices, the row index and column index, to that element. Let me show you visually how we can represent them. So basically a database relation. So here in this case, you can see a relation with two attributes A and B. So, and as I said, we can have duplicate elements. So here, if we want to represent it as a dictionary, we are going to map, for example, A1 and B1. Because we see them twice, we can map them into 2. And similarly for A2, B1. For A2, B2, we have only one occurrence of it, so we map it to 1. It's basically a dictionary from the tuple to the multiplicity. So how about a matrix? As I said, we are going to have a dictionary from the index to the value. So in this case, we only need to represent the non-zero elements, because the zero elements are basically the zero of that associated semiring. So we don't need to explicitly represent them. So basically, we can represent it with this dictionary of 3 elements, which are basically corresponding to M1, M2, and M3. So we have talked about semirings, about semiring dictionaries. We have to talk about now the query language part. And I don't want to show like the evaluation semantic of the language that we have or the grammar of it. I'm going to show you through an example what is the insight behind our language. So so here on the left side, you can see an expression in the query language that we have and the corresponding C++ code for it. So here, for example, we have a summation operator. What does the summation operator do? It's a loop. So we are looping over a dictionary, and a dictionary is a key value pair. So we are iterating over the elements of R, name them as key and value, and then in the body of the summation, we are going to say what are we adding over inside the loop. And here you can see the corresponding C++ code. So we are iterating over the elements of R, and then we are adding them together. So here in the body, we are applying F over key and value. And in the body of the loop, we can go beyond scalar values. So we can construct other types of semirings. One of those semirings is actually the semiring dictionary itself. So here, in the body of the loop, we are basically creating a dictionary. So we are adding the values of these dictionaries together. And what does adding the values of 2 dictionaries mean? It means that whenever the keys are the same, we are going to add their associated values together. And perhaps this C++ code shows the intuition behind it very well. So let me show you a couple of examples. So here we have basically an SQL query that computes the number of elements in a relation. And here the relation can have duplicate elements. So what we are doing is that we iterate over the key value pairs. So as we can have duplicates, now we have to add their multiplicities together. And that's what's happening here. So we can also go beyond just the count aggregate. We can do summation of elements. So what we do is that inside the loop, we are summing up the values of this attribute, which are actually inside the key. However, again, we can have duplicate elements. So we have to multiply it by its multiplicity. And we can do also, of course, group by aggregates. So here, for example, we are computing the summation of A, but we are partitioning them based on the value of B. So the result of this one now is going to be a dictionary from the values of B to the associated summation of attribute A. And we have the conversion of all relational algebra to the language. I don't expect you to understand it. Just believe me, we have done some work. So similarly, on the linear algebra world, we can translate them into SQL. So whenever we are adding two vectors, it's basically like adding the associated dictionaries. No magic really here. How about the Hadamard product or element-wise product of them? So we iterate over one of the vectors, and we construct a singleton dictionary where the key is actually the index of that vector. For the value, we take the value of this vector, and then we look up the associated value inside the other vector. If that one is 0, then it's going to basically make it 0, so we don't need to actually represent it. But if it is non-zero, then we are going to basically construct that particular element. And to make it simpler, we can also compute the dot product of two vectors.
Do you allow a question in between?
Yeah, I'm fine.
I was just saying, you just said we don't have to put it in there if the value is 0.
Yeah.
Done? No.
Yeah.
We don't have to put it in there. Are we allowed to put it in there? Do you guarantee zeros to be absent? How do you deal with that?
Yes. So in the runtime system, we actually normalize it. So if we see that it's 0, we don't represent it there.
Thank you.
Yes. And it's a very spot-on question, because if you want to use it for dense linear algebra, it can become problematic a bit from the semantic point of view. So again, we did a similar thing for various types of operations in linear algebra. Again, believe me, a lot of things work except the inverse. We don't like inverse. And so in the array community, especially on the functional high-performance community dealing with arrays, there is this notion of pool arrays. And here, briefly, I'm showing you how this language is connected to the notion of pool arrays. So what is a pool array? So it has an operator like a build where you specify the size of the array and a function together with it. And the function specifies at index I how should I construct the element associated with that index. And this gets translated into the following expression in SQL. So we iterate over a range from 0 to n, and then we construct singleton dictionaries mapping I to f of I. And that basically constructs this dictionary, which is actually the same thing as the pool array would construct. So we've talked about the language, the underlying constructs behind it. So, okay, we have a language, so what? We could express all these kind of things. We started all the motivation based on optimizing it. Let's see what kind of optimizations now we can do. And among all optimizations, we care more about the loop optimizations, because in most cases, basically, the loop optimizations are the ones that can give you asymptotic improvements. So we have a bunch of loop optimizations that are supported inside the language. Two types of loop fusion, loop invariant code motion, and two other loop optimizations that you usually don't see that in that many systems. I'm going to, through an example, give you a bit of insight behind what we do with this loop memoization. So let's start with an example. We have a nested loop in order to iterate over two relations, and if the join key of these two relations is the same, we join them together. That's basically a join in a database system. So an equality join in a database system. This is a naive way of representing it. However, if relation R has size n and relation S has size m, this is going to be O of m times n. So in databases, we know that they do something fancier. They do something of O of m plus n. I'm going to show you that with optimizations, we can turn this program into a program that is going to be linear cost. So let's see for opportunities. Here, we cannot really do any kind of loop invariant code motion, but there is one particular opportunity here. if we look at this snippet of the code, we can see that we can use an idea similar to the idea of memoizing a function. Or basically, it's known also as function outlining. Rather than doing inlining, we do outlining. So what we do is that we take this part of the code and we translate it into a dictionary instead. So yeah, we didn't really improve the performance here. But if we look at this program now there is an opportunity here. So this snippet of the code is now invariant with respect to the outer loop. So we don't have anything here that is dependent on these two variables. I can basically hoist it outside. And voila, what we have is basically what is known as the hash join operator in a database system. So we iterate over one of the relations. We construct a hash table based on it. And then we iterate over the other relation, and we look up on the hash table that we have created for possible joins. And this is going to be linear cost in many cases. There could be corner cases where it's still m by n. Yes?
I'm wondering about whether in general, like, how do you pick up on this specific construction? Like, is it that there's an equality to the sort of key? Is that what makes you pick up on constructing this temporary dictionary or something else?
Yeah, it's because actually in the if condition we have an equality. If we had an inequality, then this was no longer possible.
Okay. That makes
So
sense.
it's based on the insight that whenever you have an equality, and when it's similar to looking up in a dictionary, because in a dictionary also we are looking for equalities.
That makes a lot of sense. Thank you.
Yeah. Yeah, but implementing this optimization is very hard. So this is not something that you would do with a rule-based optimizer, to be honest with you. You have to use more advanced techniques, which there is a workshop there for that. So I've shown you an example of the optimization. So one cool thing here with this language is that we unify the optimizations that were independently developed across the two communities. So in the database world, there is this notion of pipelined query engines, which at the end of the day, what they are doing is similar to what push and pull arrays, or in the functional programming community, what the deforestation is doing. The insight is that whenever you have a bunch of intermediate collections that are being consumed immediately after that, we can just avoid constructing that intermediate collection, or an intermediate array that gets consumed immediately. So this is the vertical loop fusion. Horizontal loop fusion is whenever you're iterating over the same collection several times concurrently. Then you can basically just have one iteration over the collection and do all the tasks that you're doing concurrently. So in the database world, this is known as a multi-aggregator operator. In the linear algebra world, this is basically called horizontal fusion. And what we did with the loop factorization and memoization, so these are very basic optimizations that we are doing. Whenever you combine them together, it will boil down to some of the advanced operators that you see in databases, which is, for example, group join or the hash join. And in the linear algebra world, this is basically the matrix chain ordering. So the next question is that, okay, is only optimization at the level of programs the only thing that we can do? And the way that I made it, it means that the answer is no, we can do more than that. So we can also represent different types of data layouts. So in the relation world, there is this notion of row layout and columnar layout. And in the dense tensor world, there is this row major and column major. Also in the relation world, there is this more advanced notion of factorized relations or factorized databases. And in the tensor world, basically, especially on the sparse tensor world, there is this notion of more compressed representation of tensors. So we can basically represent all of them with dictionaries or with composition of dictionaries, nested dictionaries. So what we did then was that we have several prototypes of this language. So we have an implementation of it embedded inside Python. We have also an implementation of it inside Scala. There is also an implementation of it inside Julia. And we have a bunch of papers published around that. And one of them is still under review. So what about the results? So we have good results, believe me. I won't go through the detail of the results. So we have 4 sections of the results, actually 3 sections. So one is on pure database workload, one is on pure linear algebra workload, and one is on hybrid workloads. And the takeaway from here is that the SQL system is competitive, or in some cases even better, than the systems that are specialized for that particular workload. So for example, on the database side, we are comparing against 2 state-of-the-art in-memory databases. And we are competitive with them. So you could not use those systems to do linear algebra at all. They would be horrible to run linear algebra workloads. So for linear algebra, we are comparing ourselves to SciPy, for example, or NumPy. And we are competitive with them. For the hybrid workloads, there were some systems that could not support databases in general, could support only a fraction of hybrid workloads. Again, comparing with those systems, we were, in many cases, even better than them. So with that, yes?
Yeah, this is good, yeah. Hi, I was wondering whether there is a phase ordering problem when applying these rules, and did you do that manually, or is it automated?
Yeah, so to have an apple-to-apple comparison here, so for example, in databases, there is this query optimizer that does the join ordering and these kind of things. And after that, it produces a query plan. So we started from the query plan that those databases had. So these optimizations that we have seen, they would make more sense in the context of the hybrid workloads, where there is no system to do the optimization properly. And there, yes, there was a very bad phase ordering problem. And so we came up with a phase, but the phase, I wouldn't argue that it's going to work always perfectly. In the second part, I'm going to show you one solution to solve the phase ordering problem. Any other questions? So,
have you considered including another array language into the benchmark, like APL? For context, I'm an APL developer.
Yes. So it would make sense only for the linear algebra to compare against them. And so the linear algebra, so here I'm basically showing using a sparse tensor workload. And APL-based languages do not work that well in the context of sparse tensors.
I think in the J language, which is from APL, they have an implementation.
Which language?
The J programming language.
Okay.
They have an implementation of efficient sparse arrays.
Okay, that would be interesting actually to compare against. So when I was looking at it, so I was looking at FootHark, for example, and it didn't have any good sparse support like that. I know that they are working on it now.
Yeah, thanks.
Yeah, thank you. So I'm done with the most, the deepest part of the technical discussion. Now I'm going to be I become more and more shallow. And the next topic is actually the sparse tensor algebra. So we have considered these hybrid workloads. Now let's focus on tensor algebra, but a tensor algebra that is not in the realm of the array processing that much. So what do I mean by that? So we are all familiar with tensors. So in many applications, we have tensors. And recently, more and more, we are observing tensors which are basically many of the elements of which are zeros, rather than being basically many of the elements being non-zeros. And so here is where many of the techniques that people have developed in high-performance community fall short. So for example, there has been a lot of research on polyhedral compilation and this kind of stuff. They no longer apply in this domain. So the question is that, okay, what should we do? There is one slogan which every computer scientist knows, which is everything that you can see has been done in databases before. And this is basically, if you show this problem to a database person, they say, oh yeah, we have solved it. And yeah, they're not wrong. Basically, you can represent a sparse matrix as a relation. So let's consider this matrix, which is sparse. You can see many of the elements are 0. I can basically represent it as a relation with 3 attributes. The first attribute being the row index, the second attribute being the column index, and the third attribute, the value. And I can avoid representing the 0 elements. Yeah? So here, this element, which is in row 1 and column 1, associated with 3, you can see that it corresponds to this row. And for example, whenever I have this expression which corresponds to matrix multiplication, now I can represent it as an SQL query. What is the associated SQL query? So it's basically a group by aggregate. It groups by the row of the first matrix, the column of the second matrix, and I'm doing a join between the column of the first matrix and the row of the second matrix, and then I'm summing up their associated values. Yeah? So let's see how they perform. Not that good. Here, lower is better. You can see that DuckDB, which is one of the state-of-the-art in-memory databases, they're going to be around an order of magnitude slower than a system like Taco, which is the state-of-the-art for sparse tensor algebra. What is the reason behind it? So the main reason is that some of these sparse tensor tools are using data layouts that is basically compressing the representation of the sparse tensor. So here I'm showing an example from the Taco paper. So here, again, I'm using the same example matrix. So in relational databases, most of them, they are using a representation like this. It's basically a columnar layout representation of it. So they have basically one array representing each of the columns of the relation that we had seen. So if we carefully look at, for example, the array corresponding to the row, we see that there is a lot of repetition. We have 0, 0, 1, 1, 3, 3, 3. So the insight behind this compressed representation is that have some sort of encoding in order to get rid of this repetition that is happening here. So that basically boils down to a representation like this one. That makes it very complicated now, because now we are going to have arrays of different size, and size of some of these arrays is something that we have to determine in the runtime. Or more and more levels of indirection that we don't like. So what we did was that we prepared a framework which uses the language that I have shown you, STQL, a subset of it which we call STQ-Lite, in order to represent both the storage layout as well as the computation. And then we magically optimize them together to produce efficient code. So let me show you a bit of these components through an example. So here we can represent the tensor computation and the storage format in terms of this language. So let's again see, this is basically the matrix multiplication, which is actually our tensor computation. We can represent it based on nested summation. We had seen it before. So how about the storage specification? How we can represent this one as an expression in terms of STQL. So here the insight is that we represent how we decompress the storage layout. So we said that one of the insights behind this sparse tensor framework was that they compress it. So we represent a program that would decompress it into its original form. So that's going to be basically this expression that whenever we apply it into these 3 arrays, it's going to construct this matrix. OK? Is the problem solved? So we basically we are doing matrix multiplication of 2 sparse tensors. We take their compressed format, we decompress it, and then we do the computation over the decompressed stuff. It looks OK, except that not. In terms of correctness, it's correct, but it's going to be very inefficient because we had the data in the compressed format, we decompressed it, and now we are doing the computation over it. OK, how should we fix it? Fusion, let's do the fusion here and get rid of these intermediate collections that we have constructed. And as you have noted, now we have the phase ordering problem. When to apply these fusion rules that we had seen. Yeah? As computer scientists, we are lazy. We don't want to design, engineer these rewrite rules. We want some magical tool that does it for us. So ideally, what I want is that I want to specify a bunch of equivalence rewrite rules, which we have 44 of them. And for example, we have one particular rule to do the fusion. And we have another rule which basically does the factorization. So this one is very interesting because you can see that it not only does the loop invariant code motion, but it also actually puts the operator outside. So here, if we had n multiplications, we are going to have just one multiplication here. So we have 44 of these kind of rewrite rules. Then we are using the equality saturation technique. So what does the equality saturation do? You give it a database of rewrite rules. You give it a cost model. It searches. It tries to apply all these rewrite rules. It creates a search space, and then it extracts the program with the minimal cost with respect to the cost model that you gave it. And the search space it can become very big. Because of that, it basically it has a data structure called an E-graph to basically have a more concise representation of that. And on that note, basically we have, together with Mikhail, we have actually a paper in PLDI where actually we improve even the technique, the equality saturation for examples where we have variable bindings, which actually appears a lot in the language that you can see here. The talk is on Wednesday, right before lunch. So after that, when we apply this, what we have? Problem solved. Lower is better, and the most left one is us. We are not only better than the database systems, we are also better than the state-of-the-art tools. Why is it the case? It's because of this systematic way of applying rewrite rules. Now we can detect some further optimizations that was missed by some of these state-of-the-art tools. We not only do the compressed storage, we also do algebraic rewrite rules that were missing. So on the same line, to apply for sparse tensor algebra, my student Mason, who is sitting there, we have actually applied it in another context as well, which is for quantum simulation. So in quantum simulation, basically what you're doing is that you're computing a bunch of matrix or matrix vector multiplications. However, if you look at the matrices that exist in quantum simulation, you see that they are sparse, or there is some structure there. And we basically have a bunch of sparse matrix multiplications. So we have used the same language in order to capture this sparsity. And here are some results that we have. So in addition to the C++ code generator that you have seen, we have also implemented the GPU backend. And you can see that, so the rightmost one here is our tool, and here higher is better. So, and Quest is basically one tool that is highly tuned by some amazing material scientists who knew a lot about high-performance computing. So it was basically 2 or 3 work during their PhD that basically Mesa managed to do in less than a year by using this technique. And the reason for that was because, again, we could leverage some of these optimizations exhaustively that they had to basically write down each of them in low-level C code. And this has appeared in CGO this year. Okay? So I'm going to quickly go over the automatic differentiation one, just to give you a very high-level insight behind it. So automatic differentiation is something that is heavily used for machine learning, training in machine learning, where you have to basically write a compiler that automatically computes the differentiation or the gradient of an objective function. And what we realized was that in the community, there was a lot of work on automatic differentiation for dense tensors. But whenever you had some sparse tensor computation and you wanted to do differentiation over them, you would usually get some cryptic errors that you don't have any idea why TensorFlow or PyTorch do not work on them. And then whenever you dig in and go to the GitHub page and go to the issues, you realize that, OK, they don't support automatic differentiation for sparse tensors. And so what we did was that we used the same framework again, and we captured the automatic differentiation inside our intermediate language. And then because of the separation of the concern that we had, we could basically represent the storage layout also as an expression inside this language. And then we applied the same technique, and we managed to basically support be the first framework that supports automatic differentiation on top of sparse tensors. And we could basically scale it to much, much larger sizes. So I'm going to skip over the last topic because we don't have time. So I'm going to briefly say what that is about, which is basically about something in the middle of dense tensors and sparse tensors. So with dense tensors, the cool thing is that we can do vectorization, parallelization, and cache locality. With the sparse tensors, we don't have them, but instead we can have better storage layout, have better computational complexity, and scale it to much, much larger sizes. Can we combine the benefits of both these two words? And the answer that we found was that for a particular type of sparse tensors, which we call it structured tensors, where we can basically capture the non-zero elements as a shape, we can do a much better job on combining the benefits of both. And this is what we call the structured tensor algebra. So I'm not going to show the details of that, but yeah, we have work in UPSLA 23 and UPSLA this year around this topic. So just to summarize, so I was advocating for dictionary processing. So we had seen for hybrid workloads, we could represent relations and tensors with dictionaries. In particular for sparse tensors, we have seen that we could use dictionaries to represent at the logical level what the tensor computation looks like, and then how we can represent also the storage layout as a kind of conversion between dictionaries and arrays. And also the last topic that I didn't have time to go over was structured tensors, where we can capture the structure information. For example, what is the sparsity pattern, or whether there is redundancy there as in terms of dictionaries. To conclude, so data science is very important, but it's a double-edged sword. And we need to basically radically rethink about the data science pipelines. So here in this work, I mainly focused on one of the intermediate languages that we have created in my lab, which is called STQL. We have a bunch of other intermediate languages for other types of workloads where I gave pointers to them. And the nice thing here is that we can now leverage the structure inside the data, inside the language, and teach the compiler how to leverage that structure. And as a result, we can basically optimize across the data science pipeline. With that, thank you so much for your attention.
Thank you very much for the inspiring talk. Maybe we have one quick questions, if there is any left. Go ahead.
For storage optimization, have you considered inverted tables?
Can you elaborate a bit more?
So inverted tables is basically a table with a vector with columns stored as individual nested vectors. And the benefit of that is that if your column has a certain data type, having it as a single vector would just be just a simple array, which is a nicer in terms of storage.
Yeah, so that reminds me of blocked storage formats that Sparse Tensor framework has. Yeah, so this framework actually supports that. So it's quite expressive in that sense. So it can basically support many of those structures. One caveat here is that one nice thing with this kind of block formats is leveraging vectorization opportunities and or parallelization opportunities. So on that side, we are still far behind what we can basically fully leverage from vectorization. On that line, basically the last work that I didn't have time to go over actually deals with how to leverage the vectorization and cache locality better.
Okay, thanks.
Yeah.
I'm afraid we have to take this into the break, and we shall reconvene in half an hour, 10:30. Thank you very much, Amir. Again.
Thank you. Yes, and this is actually a talk combining areas of array languages and also quantum computing. So what we're going to show here is that this notion of gate fusion in quantum can kind of be modeled using the traditional map fusion as is known from the array community. This is joint work with Troels Henriksen, also at DECO. So this context here is about state vector quantum simulators and some approach that we have taken to try to implement such a simulator in the Futhark data parallel language. And it turns out that when you look at these simulators, they're pretty much all imperative in nature. They kind of operate on a global state vector of size 2 to the k, where k is kind of the number of qubits you compute on. And you have this explosion in the state vector due to these notions of entanglement and so on. I'll get back to that later. What you'll see in these imperative simulators is that the precise access and update patterns that are used to implement the simulators, they're quite advanced, and they work by using various kind of bit operations to compute the addresses inside the state vector. And then it turns out that the notion of gate fusion is quite important for performance. What we can see over here is a picture of a quantum circuit with 4 qubits numbered from 0 to 3. And then you have these different kind of gates. I'll come back to those in a moment. But what you in particular can see is that there are certain gates that just occurs in kind of in isolation and can be grouped, the T, H, and X group, X gate down there. And they're kind of, it's kind of possible that those can be fused into kind of one gate. And this is what we want to see, whether that, how that can be modeled using a simple map fusion. So our contribution here is that we are going to use well-known concept of something called vectorization. It's basically just the notion of column stacking, where there's a relation between this column stacking and then the Kronecker product of performing the Kronecker product of 2 matrices. And then we'll demonstrate also that gate operations become index transformed maps, and then gate fusion becomes map fusion. Of course, this area, we are not going to claim here that we are going to do the state-of-the-art performance in quantum simulators. There's a lot of work out there, and they kind of set the bar for quantum supremacy. When do quantum algorithms actually, when do you actually need quantum computers to actually solve real problems, and when can you just do with simulators? So of course, if you can simulate some algorithms, then or some problems, then you won't need real quantum hardware, right? And there's a lot of related work in that area. So just to show a little bit quantum here, this breakdown of classical reasoning, the double beam splitter example. Here we have kind of a situation drawn here by this picture here, where we have a source of electrons, these photons that are beamed into these beam splitters. The beam splitters here are shown here, and then you have mirrors up there. And the idea is that the classical reasoning breaks down once you add these beam splitters. So you have a beam coming in here. Half of the electrons will kind of go through, if you look at it probabilistically. Half of them go up. That will be kind of the classical interpretation. And then you have mirrors here, and they will come back here, meet another beam splitter, and then you would kind of envision that half of them would then go up and be detected here, and half of them here. This would be if you had a probabilistic view on how this would work. The problem is that this is just not how physics work. What you'll see when you do this experience is that they all come out and be measured here in this particular detector here. And that means that it kind of, the classical reasoning breaks down, the probabilistic reasoning. And instead we can model it using quantum mechanics, where a model where the beam splitters model using these Hadamard gates, and they are basically complex matrices here that are unitary. We'll come back to that a little bit. But what you see here is basically that you can model the image here with having two Hadamard gates in sequence, the two beam splitters. And what you then see is that they multiply out and they end up being the identity, meaning that you will basically have the ray just going out. And in principle, what you can see, the interpretation is then that each electron here, each photon, is basically both going that way and that way. And when they meet again here, they will basically go this way. This is how you have to interpret, and you cannot like use a probabilistic model. So just to set up a little bit more here, we talk about these qubits. They are modeled here as two-dimensional complex vectors. They specify this linear combination, and then we have these basis vectors, 0 and 1, using this Dirac notation here. And there's this property that the alpha squared and beta squared equals 1. And then the single qubit gate then becomes a transformation of such a qubit. And they are then represented by a 2 times 2 unitary complex matrix, as we saw on the previous slide, the Hadamard gate. And that just means that it's norm preserving and reversible, this idea that it's a unitary complex matrix. That means that there's a lot of gates you can write up, and here are some examples gates that are the X gate, the NOT gate, the Y gate and the C gate. They are called the Pauli gates, and then there's a Hadamard gate and the T gate down here, shown here as examples of unitary matrices that you can compute with. Now, to compose a system, we have this notion that now the state kind of explodes. So to represent 2 qubits, you would have a vector of 4 complex numbers, alpha, beta, gamma, and theta here. And then we can see that, and we still have this normalization condition here. And at a 3 qubit state, then we need 8 element complex vectors. And here we see that they usually use this Dirac notation here, specifying indices into where this is 1, this is a basis vectors shown down here in the case of using 3 qubits. And of course, when you start applying gates and so on, then these will not be just 0 or 1s. They will not be sparse. When you do something very, something where quantum is really doing something else than you could do for classical computing, then they will be kind of dense, complex numbers sitting in these states quite quickly for various algorithms, the Grover's algorithms and others, Shor's algorithm and so on. Very quickly they will be very dense. There are subsets of algorithms where you can model it much more efficiently. I won't go into this here. So how do we program these things? So here's a small gate language, so to speak, where we have gates and we have statements. The one thing you can do in such a language is that you have the different qubits here. Then you have the gates. You can apply a particular gate on some particular qubit. That is one kind of statement. Another thing is that you can swap a qubit with next qubit. So you swap q and q plus 1 in their interpretation, and that's sometimes needed to apply some of the some other gates. So here's a control gate. It will basically say that we are issuing gate G, conditioned that that we have the amplitude here for the. So here's an example of a control gate with 2 dots here. They're rooted here, and then in an X gate, meaning that if the amplitudes here are high, then this gate is performed. So that's kind of the idea of the notation, and that's specified using this control gate. Then you can have that you can put two statements in sequence, and then finally you also have a no operation gate, which can be used if you want to specify some certain kind of identities or so on. Now, looking at the circuit down here, you can write up the statement S0 down here, where that specifies basically the circuit. You can imagine writing up different statements that will specify the same circuit. As you can see, there are some possibilities of association possibilities between the statements, where you can flip them around if they operate on different qubits. So that means that there could be some algebra of making it possible to rearrange statements and still kind of give the same semantics. And we'll come back to the semantics in a moment. We see also here again that the various gate operations in the statements here, they are subject to gate fusion, as we already saw in the beginning. So how do we model these things? So one thing is that we can kind of create a big unitary matrix for the entire circuit, and then we can apply that huge unitary matrix to the incoming state vector, and that will be the main result of applying the entire circuit on an incoming state. Now it turns out that this unitary matrix is going to be quite big if we go about doing it that way. But this is still the way we want to specify the semantics of a circuit, is by doing it in using matrix multiplication from the horizontal composition, and then use tensor product for vertical composition. And here's a definition of what a tensor product means. The Kronecker product is basically just specified using this block notation with various properties, of course, that there's an identity here. And then we have the special matrices that are used for specifying qubit swapping. So we have here a swap operation. You can see here that will have to operate on 2 qubits, the swap operation. And then we have some generalized identities, and then also the controlled operator down here, where you take any unitary matrix, and then you can put various controls on top, and that is basically defined as the identity on half of the unitary matrix, and then the unitary at the inner one, also using this block notation here. So this is pretty much old. This is how it would look if you look up in a textbook on quantum computing. Now we would like to give a semantics to the statements, right? So we would like to make sure basically that the implementation we do at the end will live up to some semantics. And here's the semantics using the notation we have also already seen. Gates are denoted by their corresponding matrices, complex matrices. So you see here what you see in here is, of course, the syntax for the gate in our small domain-specific language here, and then we have the complex matrices to the right. We then also see to give a denotation for a statement, we also parameterize it over the number of qubits that we work on. And there will always be this global kind of state vector, which is 2 to the k. That means that the complex unitary matrix that we are going to use as a denotation for the various statements, they will be c to the 2 to the k times 2 to the k. Okay, and we use then the tensor product to say that if you apply a gate operation on the qth qubit, you first apply the identity on the first q minus 1, and then the gate comes, and then the identity on the remaining qubits. This is how to read this. And we also see how you define the swap operation, the control operation, and when you do a sequence, you will have the matrix multiplication. We first perform S1. This is why it's here, and then we apply S2 to the result of that. Okay? Any questions at this point? Now the question is, of course, now we can evaluate a k-qubit circuit S on a state vector by just first computing giving the semantics, computing this huge unitary matrix, and then use matrix vector multiplication to compute the result, right? So the question is, can we do better than that? And obviously there's quite a lot of simulation frameworks around that do magic things, and they are doing better than this. They are operating imperatively on the global state vector by updating the various entries. So here we are going to take another approach. So let me first introduce Futhark, a data parallel array language with various array operations. It is kind of a rich flavored language with scans and reductions and all kind of operations at a data parallel level. But what we are going to use here is pretty much just map, and then the possibility for transposing a matrix, and also to flatten and unflatten operations. So those are basically the Futhark basic building blocks that we are going to use. So Futhark has this notion of size types, which means that we can see from the type the dimensions of the arrays that the operations work on. So for instance, for map here, it takes a function from alpha to beta, and then it takes an array of size n of alpha values, and returns again an array of size n with beta values. Right, so we can track the sizes in the type. For transpose, we can pretty much see that it will swap the two dimensions here. So it takes an array of size m times n, and returns an array of size n m. Now there's some special magic going on here with flatten and unflatten. It's not really magic; it has been worked out. And we use these kind of poor man's dependent types to deal with these kind of operations. So unflatten, for instance, will assume that it takes an argument which is specified as m times n. Syntactically, there needs to be m. It can be some expression, but it needs to be a multiplication of two size expressions, m and n, and it will then return an array of exactly by decomposing the multiplication, and then constructing something of type m times n values. So that was the unflatten, and flatten works the other way around. So it takes a two-dimensional structure and a matrix, and then will basically create the flattened version of that with the outer 2 dimension being multiplied here. Okay, so we will see in the later slide. We can of course extend this thing ourselves, and in Futhark you can pretty much write a notion called vec for vectorization for vector, saying that here we take something of m times n, and then we produce something of n times m. Notice here that these sizes have been swapped here. This is equivalent to flatten composed with transpose. And similarly, you have the unvec operation, which is transpose composed with unflatten. So basically, where the flatten and unflatten work at rows, we have that vec and unvec work with columns. Now, Futhark targets.
Can I ask a question?
Yes.
So how does have you considered extending it to higher dimensional arrays, such as the leading axis theory, where you can apply a function along an axis of a higher dimensional arrays in the same fashion you do with vec and vec?
I'm not really sure I completely understand the question. Just to say that for Futhark here, we are not allowed to have functions inside arrays. So in that sense, it's not higher order. It is higher order in the sense that it can be any arbitrary number of arrays. But in the sense that alpha here can be an array type again. So in that sense, it can be, it can have multiple arbitrary many dimensions. It's not the case that it's rank polymorphic. It has some notion of rank polymorphism that can kind of at the surface level look like rank polymorphism, but it's not really defined. The inner working is not rank polymorphic. I don't know if that answers the question.
Yeah. More concretely, how would it? Well, you kind of answered it. It would generalize to higher dimensional arrays, right? This transpose these functions you listed here.
They work. It's just doing transpose is just doing with the outermost dimensions, right? It's not like in APL you have the generalized transpose where you can transpose at any arbitrary thing. You can write your own function that will do that to some down the ladder. But if it needs to be polymorphic, you will need to kind of stop at some point. If you see what I mean.
Yeah. Thanks.
Yeah. Okay. Let me continue here with. Yes. Yes, and that's what I meant by that we have a syntactic property. It's not allowed for the, so m times n is really different than n times m. And if you want to provide a witness that those two things are equivalent, you can have a small library of routines that will say that we trust these operations where you can give explicit evidence that you want to swap those things. Here, for instance, even though the numbers that are computed will be identical, unflatten will really operationally rely on the numbers m and n, right?
Sure.
So
I guess there are parameters to unflatten as well, right?
Yes,
M and N, yeah.
they are kind of implicit in that sense.
Okay. Yeah. Thank you.
So now to the notion that we can actually do better than first computing the huge matrix and then apply matrix vector multiplication. So we want to do this inductively for any statement S and integer k and state vector. We want to say that we can create an interpreter for states that immediately apply to a vector, and that needs to be the same. It needs to give the same result as if we first computed the semantics here, the huge matrix, and then applied that to V. But we want to do it without creating the vector, and we can do this using this vectorization and various properties of matrix multiplication. So here's the case for the vectorization property that one can look up at Wikipedia or something and get some reason why this works out. So here we see the vec and unvec operations in actions here. So I'm being a little bit sloppy with the notation here, but in particular we are not providing the sizes. But when you see that B needs to be possible to apply B to another matrix unvec of V, that will kind of define the size, the type of the result of unvec, which means that we can kind of infer that based on B. And then again, the other dimension is the A transpose also needs to be compatible. So with this rule and with these other rules about matrix multiplication, in particular this rule here that we can see a matrix multiplication as basically being the same as applying a mapping a function lambda v a dot v over a transpose matrix. This is identical to a matrix multiply. We can kind of calculate what it means to perform a gate operation. And we basically start by using the semantics here, up here, and then we basically unroll, and we get this code down here where we say that this is equivalent to taking the vectorization. Damn! I thought that would happen. And then mapping this function over this this thing with this particular function. Okay, so that is the how you can calculate it. And similar calculation can be done for swap and control. Now for fusion, it turns out that we want to have the property that if you have two consecutive gate operations performed on the same qubit, that should basically be identical to if we have a gate that semantically is equivalent to multiplying those two, the semantics of those two gates, then we should be able to use that gate operation instead. So that means that we can basically calculate this result, and there's more information in the paper about this, how to actually get from this thing to this thing using the notion of map fusion. And you can see, of course, under the hood that you're really using the definitions down here, and that you see two map operations in here, and using those you can basically get to the result that the gate fusion is map fusion over index transformed matrices. Here's a Futhag library for gates that that you can write. You can see the various gates here. I won't go into much detail due to time here, but there are various gate operations and so on. We can express various algorithms. Here's a notion of Grover's algorithms in Futhag specified using this gate library. We see here that there are some operations here, gate H and then gate X applied just after. Those are fused in the implementation using map fusion. And this is pretty much it. There's some notion of performance. I won't go into details here due to time, I think. And you can read more. We sometimes have a 10 times worse performance, but on GPUs. But other than that, and there are good possibilities for future work. Something we can look at to get performance even better. Thank you.
Yeah, thank you, Martin. Unfortunately, we don't have time for any more questions. We already had two very good questions, I think. So I think we should switch to the next speaker. Perfect. Thank you. Thank you again, Martin. Okay, so the next talk will be given by Professor Ganesh from the University of Utah, and it will be about challenges and opportunities in array programming on GPUs, which I think is a very interesting topic.
Thank you. Session sharing. So as was mentioned, this is a talk which tries to bring to the community's attention the fact that oh, sorry, I should do a mirror. System setting display mirror. Yeah, display mirror. Built-in display, main display, mirror. Mirror.
Yes, mirror.
Okay, thank you. Sorry about that. Yeah. Okay, so are we okay?
Can you turn off night light or true tone?
It was turned off. True
was?
tone, no, true tone was turned off.
Oh, it's already off.
Yeah.
Okay.
Okay. So welcome to this talk. Almost good afternoon. Yes. So we are in an era where GPUs rule. This is why we need to pay attention to array programming on GPUs. And GPUs are fundamental to several aspects of computing that are all highly energy intensive. And of course, we know the toll they take on our purse. Coming to some of the more familiar GPUs, they have well-recognized entities such as CUDA cores and tensor cores, delivering a certain level of performance and has a certain price point. The reason why I would like to mention some of these mundane details is to introduce some of the terminology, which is where this slide is going. Not only are the SIMT cores important, but also tensor cores increasingly, because a lot of the computation happens on them, efficient machine learning training, and increasingly also HPC workloads are being shifted to tensor cores. And they actually are occupying an increasing amount of silicon area, and there's a considerable interest in using them for HPC because of their potential to offer 8x performance boost if used correctly, if you feed the data without hiccups. This slide tends to introduce some of the terminology I'll be using. So either you write a CUDA C program with calculations such as here, a compiler takes over and produces PTEX code, which is lowered to SAS code. Or you might be interspersing matrix operations using these WMMA sync operations, which are small matrix multiplication operations. They turn to PTEX code, such as this, and they have their own corresponding SAS binaries. And these executions are carried out by warps. So if one of these operations like fmul is repeated across the threads in a warp, the entire small matrix multiply is done collectively by the help of all the threads, taking various row indices and corresponding column indices and multiplying. The reason that I introduced all this is that you will soon hear about binary instrumentation as what one of our main techniques is. And the long story short of why we need binary instrumentation is it is the honest reality. After all the optimizations are done, we get to see the effect of the actual execution that happens in hardware. And also because many of the libraries are closed source. So we really cannot understand what goes on unless we look at that level. There is nothing else to instrument. So for these reasons, the tooling that I'll be mentioning will be referring to the PTEX, the SAS level rather. But coming to the main point of the talk, now that I've gotten some of the background away, energy drives decisions in this space. This is well known. So one of Bill Daly's talks, he repeated at Hot Chips in 2023 and also at other places. He points to the fact that arithmetic takes for inference half the energy. And the trend at least is clear that math is increasingly where we spend a lot of energy. So we have to do something about that to rein in because of obvious reasons. So this actually requires us to move fewer bits. So what do? So we either trade off accuracy or dynamic range based on the number system we select. And the kind of hardware is also not uniform. Many hardware companies, custom hardware companies are gone out of business, and we get hardware from AI vendors. So this is a challenge that is going to be faced by the larger community outside machine learning, which is where we are interested in. Some of our work actually refers to, in the mission of helping DOE labs such as Lawrence Livermore Lab, which is our collaborator, trying to move linear solvers to run on these kind of tensor cores and strange hardware. So number systems essentially are the trade-off device, you can say, which helps trade off energy and also bugs, meaning the inconveniences of using inadequate representation. So if you take a look at what goes on in this area, this is a quick snapshot of the various number systems that exist. All the number formats written here. So if just let's look at BF16 versus FP32, which are 16-bit and 32-bit representations. Here you have the same largest normal number, which is the same dynamic range. But in terms of the amount of unit round off you get or the error you get, it is 16 orders of magnitude higher. So this is one aspect of how we can make trade-offs by not having enough accuracy, but having the same dynamic range. So the kind of question to ask in such a setting would be, if you actually run some HPC code with that setting, you will probably not run out of range, but you will have really, really bad error. One can actually plug in these for typical values and see how bad it gets. Or if you can use other formats which are also 16-bit, you quickly run out of range. So I think this is the real game we need to play. I'm not mentioning other esoteric formats here, where you can use for forward one set of representation, and for the reverse gradient propagation you use something different. Lots of things are happening in this area. So number systems is the playground in which we need to play and win. So how shall we do it as a programming languages community? What tools do we need? And can we all join to create some of these tools? This is where the talk is going. So I think the takeaway by so far is that GPU variety is pretty large, and debugging tools have not kept up, and the specs don't exist. This is another aspect of it. None of this is actually given to us, so we had to discover what these hardware units actually do. And also having many specs is also not good, because having a lot of specs means that you really do not know how we can move code from one platform to the other. So let's focus on three types of bugs. Bugs in the sense of issues we had to deal with, where we pay the price in terms of software correctness. So basically, the first one is of exceptions. The second is that of ill-specified hardware, and the third is that of lack of formal specification and managing their excess. So let's take a quick look at exceptions and what they mean. So it is very easy to see that even when you do a dot product, you run out of range. Even for FP32, 1.9 to 19 runs out of range. So it is very easy to get infinity values even for the familiar FP32, and less values are needed. For FP16, you run out of 16 square is out. Infinity and nans are the most serious. We'll not look at the other floating point exception types. And things like that a C programmer write like this are incorrect in floating point. It's easy to see why. If you plug in x equal to nan, the comparison turns to false. That's IEEE defined. So you get y, which is the answer, which could be 42. And if you swap x and y, where you feed the nan to y, the answer is nan. So even max is not commutative at this point. And the reality is that in a system where you have exceptions occurring, exceptions are generated, they propagate through the code, and sometimes they vanish. But by then, the damage would have been done, and this is the real problem we need to be aware of. Classical CPU era solutions do not work. CPUs are used to trap, and that's not possible with GPUs. They largely just report the exception as an exceptional value by encoding the floating point exponent field or the Mantis field. That's the story for NVIDIA. For AMD, they have a little bit of an indication of something happened in this kernel call. Nothing much can be put to use even with that much effort, that much announcement. So let us say that we just need to deal with the exceptions as a value, not as an event. So what are the mechanisms to actually see what goes on and whether it even happens? So we could take a look at what happens in very well used libraries such as PyTorch. And it's clear that, and I'll basically refer to as these aspects. So basically there are various layer types, and they have anomaly detection mechanisms and scaling steps. So there isn't a paper that I have seen that summarizes all this. This is anecdotal, and of course this is a GPT printout, let me be honest. But essentially these kinds of mechanisms are known to exist, and anyone who actually works with optimizing the machine learning compiler part itself will see the kind of issues in this area. And even the mechanisms that they provide to deal with some of these contingencies do not work, and they come with a high cost. So for instance, some of the familiar methods are clamp before the trouble occurs, gradient clipping, loss scaling, replacing infinities. Maybe machine learning systems can get away with this, even though the price that they extract is very clear. I'll mention some numbers. But what is the approach that we should take, given that this is the same hardware type that is to be supporting non-machine learning computations like HPC? This is the point to ponder. So just to call out one of these, there is a exception detection everywhere by autograd detect anomaly. It produces a 3x slowdown, so we don't want to be doing things like that. With HPC, what we have observed in a paper in 2023 in HPDC is when we deployed a binary instrumentation tool that we developed at the SAS level and applied to several benchmarks that are getting ported to run on GPU. This is a summary of over 256 examples, small to medium to large. Some of the cases we had sources available. Some of the cases we did not know what was going on because it was not code that we wrote. And in some cases we can say the exceptions do not matter. But largely the exceptions did occur, and in one case the solution itself was polluted by NANS. And then we had to ask a numerical scientist saying, what do we do? They said there's an API in this library called boost diagonal, apply it, and sure enough the exception vanished. That allows the numerical scientist to get to the next stage in their experimental pipeline. But this is not a long-term viable solution that we would agree. So what is the standard that we should aspire to? This is something that the PL community has to actually articulate. One of the simpler definitions that I have seen with which Jim Demel has put out is that of sound or consistent exception handling. And he has applied it to construct BLAS routines. So he actually shows several BLAS primitives, and what is required is that the exceptions are either correctly handled in the code or at least manifest at the output of the function. And without that, we cannot really work with it. If it silently disappears inside, that is not a well-designed module. Of course, if you look at Jim Demel's report, it actually becomes clear how much the code increases in terms of incorporating this measure of proper exception handling. They have a really nice paper on how to spoof exception values and find this. It's a very neat technique, but it doesn't seem to scale. It perhaps would not scale. I haven't tried it, but my mental math says it is not for large piece of code like we are talking about. So I think the gist of this talk is to see how the tooling looks like and what the dangers are. And I'm hoping to show you where we are at least in the exception land, and we'll come to the other two aspects of bugs that I mentioned earlier. So the instrumenter that we have built, this is the old tool, GPU FPX, is available. So if you grab that URL, it's also available on my homepage. Is able to find exceptions on SIMD cores. So even building this tool required us to understand what the SAS instructions mean, where the actual implied operands are, where the results are delivered. None of this is known. Sometimes there is a register mentioned, but the next register is also implied, things like that. NixNAN is the name that we are hoping to impart for the next tool. Sorry, question? No, okay. Yeah, so this is a tool that we are building for tensor cores, where the task is that of grabbing exceptions from every lane and then packing them into a unified word. That's also available. It is a new tool that we need to put to use, so I invite you to try it. So how does a tool like this use in terms of look in terms of usage? It's pretty simple. So if you look at the left-hand side, I'm training a simple n-gram DFA that the GPT that Karpathy designed is learning. So it's learning the language as an n-gram state machine. So the training finishes, and it finishes in about 2 seconds. What happens is to use the tool, all you just do is a LD preload of the analyzer, and then the same command. So at that point, the instrumenter is ready, armed in action. Whenever a kernel launches, it looks for floating point instructions that generate exceptions, and then it reports a summary of the exceptions. So in fact, you can kind of X-ray down the stack and start seeing which kernels are getting visited, what exceptions they're reporting. And the net effect is that information plus slowdown. In this case, it finishes in 4 minutes. So that is the slowdown you can expect. This is a highly intrusive process, but it works in pretty much all the cases. Does it do consistent exception handling? The answer is no. A lot of exceptions happen. None of them seem to be in the final answer, not in the loss function. Of course, it happens. When it happens, people actually notice, and they do something about it. So you can even do a casual search of PyTorch, AutoGrad, exceptions, NAN, and you get thousands and thousands of hits. So the community is paying the price. It's clear. The kind of reports we get like this are somewhat useful, and I'm not making any pretense that this is the ultimate stopping point. We all need to work towards it. But as a hilarious experiment, I took these scripts that were produced and uploaded to GPT. And it seemed to understand that this exception can be interpreted. And it actually told me that these are the kernels in the PyTorch that are involved. And it even gave me a severity rating. Take it with a lot of salt. But the real news is that if you have a captive agent that goes with the framework that you're building, maybe it will learn over time the kind of traces and the bug fixes that you manually did. In any case, there is a real need to triage and attribute severity level to these exceptions. Not all exceptions matter, but some of them do matter. This is where we need to be as a community to understand and have a systematic way to do it. One of the examples I'll tell you is an open issue on GitHub that my student looked at. And it was a simple recurrence unit where the issue was not fixed. So the relevant piece of code looks like this. It's a piece of Python code. So we applied the instrumenter, and it actually does a flow analysis through the instructions, saying where are the exceptions getting sourced, where do they conduct, where do they disappear. And in this example, we learned that the exceptions were present very early in the tracing. And with some head scratching that is inevitable, we knew that the exceptions were sowed by the fact that the data was not properly initialized. The person allocated a tensor thinking that the memory will get cleared, but that doesn't happen. So if you change it to torch rand like that, the exception goes away. So at least there's some value in understanding that it might be a mistake that you made in your code. Basically, that is about what I can say. So there are 4 or 5 experiments I have presented in the paper, 2 involving lossy data compressors, and all of them have this possibility of generating exceptions, and the tool is able to at least tell you what kernels are involved, and this is the direction that we have started, but I don't think the community is fully engaged in tracing. There are LLVM level tracing tools, but that can probably help at a level where LLVM is available. Changing gears, we are now going to briefly spend some time in terms of lack of specifications and what do we do with too many specifications. That will be a few minutes spent on each of these topics. Tensor core operations are able to support operations of this kind, d equal to a times b plus c. The kind of math involved and the rounding rules are being discovered. There is a set of papers by Fassi and Mantas Mikaitis, Nicholas Hayam, the late Nicholas Hayam. They found out that the FMA operations are applied blockwise. So if you have a dot product, you chunk it up into size of 4 or size of 8, and for each chunk of 4, the dot products, the times and plus have 1 rounding error, so like that. So between blocks, there is no FMA effect. So the block width actually becomes apparent when you actually use it, and it can be dramatically shown by creating a simple calculation like d equal to c minus ab, which occurs in many linear algebra codes. And we looked at the intended math and filled all these matrices C, A, and B with the values that we made, my student made. And we could make these 3 units and the CPU produce 0 as the final answer on an 8K by 8K matrix. On an MI 100, we made it produce 255, and on H100, we made it produce 191. So the kind of answers, these little errors do add up, and 8K by 8K is not large. So if you get numerical variability of this order, it's not in the last third fractional digit, it is in the 3rd significant digit that they are showing, which is far higher. So this is the kind of danger we will face if you don't have a calibration for the hardware. And there are tests that we have devised to discover specifications. So this is a test that runs through tensor core and finds out the block FMA width, which is not known before. And we have published these tests also. This was in a paper last year. So the kind of specifications we have discovered are of this kind. So if you look at precisions and GPU types, we have discovered variations in terms of where the subnormals are handled or not. We have discovered how many extra bits are kept in the floating point rounding, because for round to nearest, you need 3 extra bits below the LSB of the mantissa, but that's not present always. So you cannot expect certain rounding modes. Then the block FMA width changes. So I think the fact that the calibration is not there is a big worry. That's the news here. And let's now look at further problems that the lack of specification or even having too many specifications might create. It is going to affect our ability to understand devices, auto-generate code, verify auto-generated code. All these things are going to be affected by either a lack of specifications or lack of specifications. So for instance, this is a piece of code that GPT generated to find the max element of a matrix. It uses shuffle sync and highly optimized instructions, and this code seems correct, and the human scrutiny told us it is correct. But in another instance, Claude generated a piece of code like this, where it was scheduling work for an inactive thread in a warp. So that is obviously buggy. So even for short, pithy, fast codes like this, if we have an SMT specification maybe for the instructions, perhaps we can hope to verify some of these codes that will inevitably get used by people. If we don't give them the tooling, they will have possibility of bugs in their system. This is a paper that a collaboration between Rochester and Utah resulted in this paper. We have an SMT model for 3 generations of tensor cores, and the student won a best paper, so this is worth looking at. This is where the surfeit of specifications will start affecting. In our current work, we are actually taking linear solvers and porting them to run on strange hardware. And iterative refinement is one of the modalities where low precision is going to be used, low precision hardware is going to be used. So we'll core solve the X equal to B. This is a highly published, well known in the numerical community. Compute the residual and then solve for the correction term, update the solution. So this is kind of iterative refinement scheme, and various other schemes are proposed. And the question now becomes, what precision choices would you make for all these steps, and under what condition would such a linear solver deliver results reliably? This is where the HPC community has to head anyway. So I'm done. The challenges are, we really have coming to us all the high performance hardware without too much tooling. The community is also largely unknown to us. We hope we can form a community around workshops like this. We are offering some tools that you please should try and help us improve. Let us make the tooling in this area strong, and also start building formal specs. If we have a library of specs that we can build, we can probably share, and the community will at least be able to match up to the, I mean, at some point the communities, companies have to cave in and provide us more, but I don't know when that is happening. And last but not least, we really need to know how to emulate when there is a variety of hardware, how to port applications across without surprises. I think that pretty much summarizes what I had to deliver today. So thank you. So
thank you very much. Thank you. So we started a little bit late, so maybe we can take one question.
There's one question there.
Oh, awesome. Thank you. I guess in terms of what kind of spec do you want? So I think, one, I'm at NVIDIA now. Yep. And I think one of the questions that we've been doing specification stuff around the Tensor Core, yep, and how do we communicate it is maybe the big open question to me, because some amount of variation per generation will happen. Yes. So like, we could go the extreme way of something super formal for every single release and try to get it really precise. Yep. There will still be bugs, et cetera. But then also, what is kind of the bounds is like, do you want a guarantee that is forward compatible or future? So I don't know, but that would be a useful thing we can talk about offline as well, but if there's something in your mind.
I think this is a wonderful topic. I would say one could look at the variations that are possible. So multi-term adders exist, rounding modes exist, several combinations exist in terms of which exceptions are reported, which subnormal types are handled. Maybe start putting cocktails of these and say for this cocktail, this is what one can expect. Maybe one has to make it generic and then bind to the actual hardware as and when occasion demands. And tensor cores are a fast-moving area of NVIDIA's landscape because of obvious reasons. So concurrency is a big deal, which we have sidestepped. So I think both have to play out very well. So, yeah. I'm available later, but I hope the basic message is clear. Thank you so much. Yeah.
Okay, let's thank the speaker again. Thank you very much. So the last talk will be given by Mathieu about neural networks, static analysis of neural networks and its acceleration. So let's not waste any time. Thank you.
Okay, can you hear me? Okay, so this work is about accelerating the static analysis of neural networks by what we call batch representation of abstract values. For the general context, as you know, IA is increasingly used in critical embedded systems, and what we would like is to have some safety properties like what we have for usual software. And in this context, we want robustness properties. So we want to prove that small changes in the inputs will not change significantly the outputs. And we want explainability, which means to understand why neural network is giving some answer. So this is the kind of things we are interested in. And to obtain these results, we are using abstract interpretation techniques. Why we do that is because since abstract interpretation is formal method, we can have guaranteed results. Another advantage is that we can work on sets of inputs, not on single inputs. We can reason on sets of inputs in a one single analyze, and also we can answer to our question concerning robustness and explainability. In the Numalis is a company which develops software for that, and when we have abstract interpretation tools for these questions. Anyway, there are some disadvantages in these methods. Is that for the abstract interpretation to be precise, we need to use abstract domains which are relational, and this is costly. It is very time-consuming and mostly memory-consuming. The most important bottleneck is the memory, actually. And another disadvantage is that the abstract interpretation does not work with standard values, with floating point values. We have to use these abstract values. And so we cannot use the inference, the interpreters that we have in the libraries like TensorFlow, PyTorch. We have to re-implement our own interpreter which works with abstract value, and this is time consuming, and we cannot optimize as much as these framework do. Okay, so if we go a little bit into details, what we want to do is to take a neural network, which we can view as a function from Rn to Rm, and some abstract value in the input domain. And we want to compute the smallest convex envelope of the result. So we have one strong requirement, that is that we want to be sound, that is we want to enclose the actual image of a result. We can be over-approximating, but we want to have an enclosure of the exact result. And we also have, so this is a strong requirement, but we also have a weaker requirement, which is about precision. We want to have the smallest possible convex set, obviously that satisfies the soundness condition. This is to minimize the over-approximation. Okay, so this is our problem. In the context of neural networks, if I give some example for a classifier, if we execute if we do some inference with a standard value, we would obtain the red result, a weight for each class at the end of the network. And instead of using an image, we are going to use a convex hull around this image, for example, by putting one interval for each pixel. And so we will obtain an interval for each class in the output. And in this case, so this is the lower bound and the upper bounds are given in blue. In this case, we can say that we are robust because the lower bound for the dominant class is still higher than the upper bound for the second class. And in addition, what we can obtain is these red points on the image, which say which pixels have contributed the most to the classification. This is this is what we call an heat map, and it's a way to explain why the answer of a network is what it is. It's because of the red pixels. Okay, so before going into the contribution, I need to introduce some material about affine forms, which are the abstract domain that we're going to use. So there exists many abstract domains when you do abstract interpretation. One of the simplest one are the interval arithmetic, which graphically correspond to boxes, that is with intervals for x and y. If you are in 2 dimensions, then you can define a rectangle or an hyper-rectangle in n dimensions. And there are many other domains like polyhedra, like octagons. But what we are using here are affine forms and the affine arithmetic, which graphically corresponds to zonotopes. Zonotopes are forms like this one, which are, there is a central symmetry around, with the central point of the polytope. What we can see is that there are relations between variables. For example, this line here corresponds to an affine relation between x and y. So we are more precise. We introduce these relations to be more precise than intervals. Affine forms are very practical for neural networks because they are very precise as long as you have linear computations, and this is the case in most computation in neural networks. Even obviously there are non-linear layers. So from a more mathematical point of view, we can introduce an affine form like that. Let's start with intervals. An interval can be represented by its center and a ray, and it corresponds to the interval C minus R and C plus R, where C is the center and R is the ray. You can see an affine form as a center plus several rays. So there are different sources of approximation that we call noises, and we keep them independent to keep more relation than in a simple interval. So we have a center C, and we have several rays of intensity alpha, and these alpha are values, are the intensity of a noise, and the epsilon I is the noise symbol. It's a formal variable that we just evaluate at the end when we want to compute the concretization, the interval value of a affine form. And this concretization is C minus capital R to C plus capital R, where this capital R is just the sum in absolute value of the intensity of the noises. So we can compute with such a affine form. For example, here I have a vector X of 2 affine forms. We have the center 1 and 4, and next we have three noise symbol, epsilon 1, epsilon 2, and epsilon 3. And then we are going to compute WX plus B. And for example, the new center here, 7, is obtained by doing 2 times 1 plus 1 times 4 plus 1. We obtain this 7. And if we watch at the coefficient, the noise, the intensity of the noise of epsilon 1 in the result, it's, it is 2 times epsilon 1 minus epsilon 1. And so here we are going to reduce the noise by this subtraction because we know that both noises are going from the same source, epsilon 1. So we obtain these results if we compute the concretization for the first dimension. We have 1 plus 4 plus 1 in absolute values, so it's these terms makes 6. We have 7 minus 6 to 7 plus 6. Okay. Next, we have to work a little bit more for non-linear terms. So if we take a simple non-linear function like this one, x to the square minus x, and we assume that x is between 1 and 2. So in a fine form, x is between 1.5 plus 0.5 epsilon 1. If we developed the term x to the square, we obtain some second order terms, 0.25 epsilon 1 to the square. And this is not an affine form. We cannot have squares of noise symbols. So we replace this epsilon 1 to the square by a new symbol, epsilon 2. Doing so, we introduce over approximation because we are losing the relation between epsilon 1 and epsilon 2. But anyway, we obtain a new affine form. And if we compute its concretization, we have something which is more precise than what we would have with intervals. Okay, so we're going to use these affine forms for the analysis of neural networks. And here is the point where we obtain very big arrays. You have to see that we are going to associate one noise symbol to each pixel of the input. So if we have, yes, okay. In addition to this, we will have new noise symbols for all the nonlinear computations. So we start with many noise symbols and we introduce many others during the inference, the abstract inference. So even if we affine from a few noise symbols at the beginning, after a few layers, all the noise symbols, because of the combinations, all the affine form will have all the noise symbols. So this is a lot of data. So we also merge some residual, some of the new noise symbols into residual symbols to limit that. So, but it introduces also over approximation, but we limit like this. But we still have many noise symbols. For example, at the beginning, we take the value of a pixel and we generate an affine form whose center is the value of the color and the noise is a percentage of the intensity of the pixel. This is what we do if we want to have a kind of white noise, but in practice we can use more sophisticated noises. Okay, so we have many abstract affine forms like that, and what we want to do is to collapse them to limit, to have a better representation. So instead, if we just write a simple interpreter, each affine form will be represented by a kind of list, or an array, but a data structure which contains the center and all the noise symbols. And we will have to re-implement the addition, all the multiplication by constant, all the functions for these affine forms. And we will not compete with the best implementations that we can find for tensors. So the idea of batch representation is to revert the problem and to put all the centers of the affine forms into what we call a batch, and that will fit into a tensor. Next, all the noise symbol in multidimensional tensor, and also the residual symbol in another tensor. This enables first to use the tensor implementations of the frameworks, and also to do parallel processing. We're going to see that. So what we do, we take our affine form. We have many of them. For example, for an image of size 224 for the height and the width in 3 dimensions, we already have more than 150,000 noise symbols. This product is more than 150,000 symbols. And so what we are going to do is to create a tensor AC for the centers, another multidimensional tensor for the noise symbols, and also for the residual symbols, another tensor. And what we show in the paper is that we can, the affine operation on affine forms, for example, if I have a set S of affine form encoded in a batch, then the affine transformation of this set of affine form can be decomposed and can be computed in function of AC, A epsilon, and AT. We can do this for linear operation, for convolution, and for addition of subtractions. So, doing so, we can just write our abstract operations as tensor operation that can be directly implemented using the libraries. Okay, and this also works for nonlinear operation. It's a little bit more complicated. We have to introduce some intermediary terms. This is described in the paper, but we can compute, for example, here the value of a batch of affine form in function of the batch of the arguments. This also works for other non-linear functions, and some of them are given also in the article. Okay, and using this, we can define an algorithm, which is also described in the paper, to define our abstract inference, our abstract interpreter. And what is important is that most of the real operations are operations on tensors. Okay, so this enables us to obtain good speedups because we rely on the library, and as we are going to see, we can easily parallelize what we are doing. So the first measure is to compare what we have on a CPU execution and what we have on the GPU execution, and we can see that we have significant speedups. What is interesting here is that there is no effort for the parallelization because it is just using the parallelization proposed by PyTorch in this case. So we don't work on the parameterization. We just reuse the best parameterization proposed by the library. The work was before was to represent our abstract value in such a way that we can it can fit into tensors. This is our contribution. And next, the parameterization becomes trivial for us. Okay. And the method has so this is data parallelism, but our method also allows to do task parallelism. Since we can the computation are independent on the different components of a fine form, then we can create several batches. This is a part of the noise symbols, this is another part of the noise symbols, etc. And we can do task parallelism. We can parallelize the computation of the operation on the abstract values. Here it's done for workers on the schemes. We did several experiments, and what we can see is that we have a rather good efficiency. If we compare, for example, between 1 worker and 4 workers, it's not 4 times faster, but not so far. So we have a good task parallelism. We didn't have a machine to do it, but the task parallelism and the data parallelism that we use are compatible, can be combined, and we could put both kind of parallelism and obtain even better speedups. Okay, so this is another illustration of what we obtained for 2 size of images. It's the execution time in function of a number of workers. It's an overview of the data which are given in the table on the slide before, and we see that we can win a lot of time by parallelizing. Okay, so to conclude, that we'll say that this batch representation, the idea really is to compute differently with the abstract value to make them fit into tensors in order to reuse all the machinery that we have in libraries. It is possible, and it enables to handle larger networks faster. We benefit from many work done by others. Yes, okay. So in practice, a fine form are not the only abstract domain that we use. So we this work has to be adapted also to the other abstract domain that are used for the abstract interpretation of the neural networks. The problem of abstract interpretation of neural network is huge in terms of scalability. So there is not one method that can solve all the problems. We also have to use other techniques, for example, to merge symbols cleverly to avoid to have too much over approximation, and also to work on the representation, the memory representation, the data structure to have limit the memory size that we need. Okay, and that's it. Thank you for your attention.
Let's thank the speaker. I think we have time for 1 or maybe 2 questions. Yes, please.
Hey, Matthew. So if I understand correctly, when you batch it, you start with the center value for the input batch. And then when you proceed further, do you do anything different in terms of addition of noise variables, or is that still the same, the introduction of noise variables?
It's interesting. For now, it's the same. But I think that we could add over approximation that would reduce this symbol at the same time. And so we could combine the reduction of the number of symbols with the batch representation to have more efficiency at the price of some unprecision. But it is interesting, yeah. No, for now, but for now it's the same number of symbols.
More questions? No more questions? Okay, then let's thank the speaker again.
Thank you.
Okay, let's start. A very warm welcome to the first afternoon session of the Array Workshop 2025. We have two talks in this session, and it's actually, I was convinced it's only one talk. Although we have both speakers here, Ari Rasch and Richard Schulze from the University of Münster in Germany. But it's going to be just one talk for 1 hour, and it's all about multidimensional homomorphisms and what you can do with that. The floor is yours, Ari.
Thanks a lot for the introduction, Clement. Just adjust this.
Oh, you can keep it.
No. Now better?
Yeah.
Okay, perfect. Okay, yeah, thanks for the introduction, Clemens, and particularly also a big thank you to all organizers and potentially also reviewers if they're here in the audience for giving us this opportunity of having this talk here today. So as Clement already mentioned, so I will present both of the talks that have been intended for the MD8 session, and since both talks are highly correlated with each other, I've just prepared one self-contained set of slides, which makes things, I think, a little bit more fluent and compact here. And actually, the second talk was intended to be presented by my colleague Richard. He's today also here. So Richard is responsible for a lot of technical things that I will present in the talk. And if there are any questions, he will surely be able to answer that. And yeah, I also might need to mention, so I will be mostly presenting existing work and also work in progress results. So that's not original work that we are presenting here. But particularly regarding the work in progress results, every kind of remarks, questions, even if they're mean, so they are highly appreciated. So we had also a talk, I think it was 2 years ago at the Array workshop, where we had some lively discussion that really helped us a lot to shape our way in this direction here. So please feel free to ask any kind of question. And I can also, of course, take questions in between, so they don't need to be at the end. I think this entire talk will be like so 40, 45 minutes at most, so that we should have plenty of time for questions at the end. Okay, but now let's start. Yeah, maybe just one quick slide so that you know who we actually are. So Richard and me, and also the two Hunlo brothers that you can see here in the bottom, we are a group, and we are working on the MDH, ATF, and HCA project. And these are approaches toward generating, optimizing, and executing code for data pair computations, such as, for example, linear algebra routines, stencil computations, and all these kind of deep learning operators that we are seeing nowadays a lot. And this computation in the context of contemporary parallel architectures, such as, for example, GPUs, CPUs, and so on and so forth. And yeah, the two Hunlo brothers are mainly involved with a lot of implementation, so they can be considered as kind of software engineers in our project. So they are doing a lot of things regarding MLR. So they mainly try to bring the concept that we develop into the MLR project. That's what these two guys are mainly doing. Richard can be considered as the main technical engineer in our project. So everything that's related to implementation that you will see in the following, that's apart from the MLR stuff, is all done by this guy alone. So he's really doing a great job here. And yeah, I am something like a project coordinator or leader. So I started this whole thing, and I'm responsible more for the higher level concepts, having the big picture in mind, giving these kind of talks, writing the papers, and these kind of things. So yeah, now I hope you have a rough overview of who we are and what we are doing. And okay, and the focus today will be mainly on our research on MDH, so our research on how we generate code and code generation stuff. I have like 2 or 3 slides about our ATF approach, which is about code optimization, so that you have at least seen it once, because ATF is not specifically tied or bound to MDH, so it's a kind of an optimization engine that can be used for any kind of project, so potentially also for your project. That's why I wanted to just present you what's ATF about and how it's used kind of quickly and roughly. And actually don't have slides about HCA. So HCA is our research on code execution. So that's mainly about host code optimization. So CUDA host code, OpenCL host code, high-level abstractions for programming these kind of host codes, how to easily express optimizations. I think it's also an interesting project, but for time reasons I had to skip the HCA project out of the slides here. So the goal of MDH and ATF. So MDH and ATF are approaches to generating and optimizing code for data parallel computations. And if you just want to summarize kind of quickly in simple questions what these projects are about, the questions would be regarding MDH, so our code generation, our research on code generation. How can we generate code that can be fully automatically optimized for a particular target architecture and also characteristics of the input and output data, so such as, for example, the data size or memory layouts? And our research on ATF, so the second part of our research immediately follows up on this question and is now about the question, okay, we have generated code that can be fully automatically optimized according to MDH. How can we now eventually optimize it? So ATF is mainly about techniques from automatic program optimization, numerical search techniques, how can we represent search spaces so that they don't, efficient representation for search spaces, how can we explore these spaces, why the MDH part of our research is more about programming languages stuff, so formal semantics, domain-specific languages, search space specifications, or how it's a search space needs to looks like rather than how it is expressed, which is part of ATF. So that's how you can think about these two projects here. And yeah, the ultimate goal of MDH and ATF, and actually also HCA, which is not on the slide yet, but is to simultaneously achieve performance, portability, and productivity. And by performance, we really mean we try to achieve performance with this approach that is competitive to end-optimized solutions. So like, for example, NVIDIA QBus and QDNN, Intel 1MKL, 1DNN. So we don't have to try to have some kind of trade-off between performance and productivity or these kind of things. By portability, we mean both functional portability, but also performance portability. So with a program expressed in our approach, so with the same program code, we really try to achieve a consistent high level of performance over different kinds of architectures and also data characteristics. And productivity here means we want to free the user of our approach from any kind of hardware and optimization details. So that, for example, an AI scientist, a chemist, a physicist can completely be focused on its particular domain. Okay, now regarding MDH. So we have a website about MDH, so if this can somehow gain your interest, please feel free to check out the webpage about MDH, where we have a lot of examples, some illustrations, also some linkings to code example and these kind of things. And if you prefer reading a paper, we have a bunch of paper about MDH, but I think the top last paper from last year that actually was also presented at PLDI last year, we consider this one as the main MDH paper here. So the goal of MDH. So first of all, MDH is a formal framework for expressing and optimizing data parallel computations. And for this, MDH makes three major contributions, which are MDH introduces a high-level program representation. And first of all, as part of this representation, we have tried to come up with a formal notion of data parallelism. So for example, data parallelism, I usually was struggling with this term because we have an informal definition like applying a function independently to data. Then we have a lot of examples where we say they are considered as data parallel, like matrix multiplications, convolutions, but there was never really a formal definition. So the first thing that we tried is to really clarify what we understand as data parallelism in a formal way here. And maybe more interesting for today, based on the common algebraic properties of these computations, we have defined higher order functions for conveniently and uniformly expressing these kind of computations, fully agnostic of hardware and optimization details, while we still capture in the representation all the information that are relevant for eventually generating high-performing code. For example, in CUDA for GPUs or OpenMP for CPUs, and so on and so forth. So the second major contribution of the MDH approach is the low-level program representation. And in this representation now we really try to explicitly express and reason about optimizations for the memory and core hierarchies of modern parallel architectures like GPUs and CPUs. And we also try to generalize these optimizations that they apply to arbitrary combinations of a data parallel computation and a parallel architecture here. And yeah, the last contribution of MDH is kind of a natural success of the two first contributions. The third contribution is a structured optimization process that fully automatically lowers an instance in our high-level representation to a device and data optimized instance in our low-level representation, based on auto-tuning actually, and that's, for example, where our auto-tuning ATF will come in the game, as you will also see later throughout this talk here. And yeah, again, so the focus today will be mostly about on the high-level representation of MDH, so mainly how MDH is used. I have like one slide about the low-level representation and one slide about the lowering process, so that you have at least seen it once, but the major focus will be on the high-level representation, so how MDH is actually used from the user perspective here. So MDH high-level representation. So while we have designed our high-level representation, we had three major goals in mind, which are, it should be uniform, minimalistic, and structured. And by uniform, we mean it should be able to express any kind of data parallel computation without relying on domain-specific building blocks. So we don't want to have building blocks, for example, in our language design, mostly focused on linear algebra routines, and some building blocks mostly motivated by, for example, central computations. And if someone comes up with a different flavor, I say, of data per computation, then we need to extend our language design, incorporate it into an optimization system. So we want to avoid these kind of issues completely by scratch from design here. Minimalistic means we want to rely on as less building blocks in our language as possible to keep the language simple. Simple for the user, of course, that uses our system, but also for us developers that need to eventually generate code from these blocks here. And structured means we want to avoid composition and nesting of these building blocks as much as possible for expressing computations, thereby again further contributing to the usability and simplicity of our language design here. Again, for the user, but also for us developers. So now we could show, that's also discussed in detail in the paper, that we only require 3 higher order functions to uniformly express any kind of data per computation. And these higher order functions, you can see it on the top, it's a simple overview here. These are InView, MDHOM, and OutView. And InView is always responsible for the input data. So there we specify the data accesses, and they mainly transform the domain-specific data representation, like for example scalars, matrices, vectors, and so on and so forth, to an internal data representation. MDHOM is always responsible for expressing the data per computation, and OutView brings the internal data representation back to the domain-specific representation here. Okay, how does it look like for a very simple, but I think still illustrative example like matrix vector multiplication? So on the top of the slide, you can see how matrix vector multiplication is expressed in the MDH formal high-level program representation here. On the right side, you have a straightforward C program that's completely equivalent to the expression that you can see here on the top. Parts that corresponds to each other are highlighted in the same color. And yeah, what's happening here? So InView captures the access to the input data. So in this example, we say, okay, we have a matrix M, we have a vector V, and at each point of the iteration space, we access a matrix at position ik and the vector at position k. MDHOM now expresses the data per computation part, which is applying multiplication to the accessed matrix and vector elements. And then it says, okay, results, so the obtained intermediate results are combined in the second dimension, so the so-called k dimension of matrix vector multiplication via pointwise addition. So that's denoted as a plus symbol here. And we combine the results in the first dimension, so this so-called I dimension of matrix vector multiplication using concatenation, which is denoted as a double plus here in our formalism. And yeah, the output view is actually instantiated trivially in this example, but it can be used in, for example, more advanced. Yes, please, Clement?
I already have a question.
Okay.
If you look at the V colon IK, does it mean, how does it should I interpret this? You said this is the access pattern to the vector. It looks like a 2-dimensional access pattern.
You mean
the right-hand side of the top box.
This one?
Can you repeat the question? Is this for the recording?
Oh, sorry.
Yeah, you can use your microphone as well.
Yeah, okay, I can repeat the question. My question was about the bottom right part of the upper box with the access pattern to V, which I would interpret as a 2-dimensional access pattern to a 1-dimensional data structure.
That actually maps the iteration space to the majority of the data. So here we say, okay, I, K are indices of the iteration space, and then we map them to the K. So this I and K, you can consider them as this I and K, and this K here is this K. That's how the relations between, or how these index functions can be interpreted. Any further questions so far? Okay. And I think I stopped by the output. So the output view in this example, so the output view is trivial in this example, but for example in matrix multiplication, the output view can be used to solve the result matrix as transposed or the like in a very structured way. And yeah, maybe as an interesting side note, we could even show that due to the minimalistic and structured design of our language, so we can even generate these kind of expression, as we can see here on the top, even from straightforward sequential code, so for example in Python or C. So we can just take as input the program that you can see on the right side with a simple annotation, and we can generate exactly the same program as you can see here on the top. And also, of course, for more advanced examples than just a matrix vector multiplication. And yeah, so in the paper we could show that we are capable of expressing various kinds of data per computation that actually differ in significant characteristics here. So for example, we could show that we can express linear algebra routines like dot products, matrix vector multiplication, matrix multiplication on transposed matrices, batch matrix multiplication. And actually we could even show that these these expressions for linear algebra routines are evolve very naturally from each other, which is kind of intended, because, for example, a matrix vector multiplication can be considered as multiple times computing dot. A matrix multiplication is like computing multiple times matrix vector multiplication. And that's exactly reflected even in our formalism or in our formal representation here. Then you've also expressed a further example, like for example convolution stencil, convolution-like stencil, Jacobi stencils, which differ from linear algebra routines by accessing neighboring elements in their input data. Then we have quantum chemistry computations, probabilistic record linkage, which is an important example from data mining and used to identify duplicate entries in a database, histogram computation, map-reduce pattern, prefix sum computation, and so on and so forth. So we consider this as a diverse set of different data pair computations here. And yeah, what might be interesting, so kind of quickly and short to the point, so what's the difference between MDH and other kind of representation? So just regarding MDH high-level representation without the low-level representation and the lowering. So another representation that's kind of popular and very heavily used is a linear representation of the MLR framework here. And for example, compared to MDH, the two major differences that we see is so first of all, MDH explicitly captures the operators for combining intermediate results. So for example, in the case of matrix vector multiplication, we have seen that we explicitly express the pointwise computation, so this plus that's highlighted in red here, so that we know what's the operator to combine different intermediate results in this dimension here. Compared, for example, to the linear program, it just says it's a reduction computation, but reduction can mean anything. So we don't have access to the operator, and so there's less semantic information captured in this representation, which complicates generating efficient code. So for example, if you want to also optimize and parallelize reduction-based computations within the actual target computation here. And a further interesting or important point is that MDH clearly separates the scalar operations from the operations for combining intermediate results. So in our representation, we separate the multiplication, so the so-called scalar operation in MDH, from the addition and the concatenation. While in the linear representation, they are kind of fused together in the body of the linear generic. So this body of the linear generic can be kind of considered as a loop body here. And of course, for simple matrix vector multiplication, you might be able to make a semantic analysis of the body and extract these operators. But for already slightly more complex use cases that might become much more complicated, and in the general case it's even impossible according to the Rice's theorem here. And yeah, we can exploit this additional semantic information in the MDH representation to achieve higher performance, for example, by also parallelizing and optimizing reduction-based computations, and it also contributes to higher expressivity because for example, in MDH you can use different kinds of combine operators. So for example, a pointwise with a prefix sum that's, for example, required to express maximum bottom box sum. The maximum bottom box sum example, that's also kind of an important example here, which is not possible, for example, in algebra. And yeah, if that somehow could gain your interest, or if you're working with the linear dialect and want to have a little bit more information about that, so we had a presentation last year at the Euro LVM, and the slides are actually linked here. I don't know if these slides go online, but if so, you can easily find them. And maybe also maybe kind of quickly a comparison of MDH with TVM, which also kind of, or maybe this state-of-the-art approach for generating efficient program code from these kind of high-level abstractions for array computations here. So compared to TVM, the major strengths of MDH is again mostly regarding the combine operators here. So MDH allows using different combine operators, and we have a formally defined semantics for them. And we also allow, so using different kinds of combine operators, and we also allow to use arbitrary kinds of combine operators. For example, TVM is limited to a set of predefined operators here, while MDH actually allows you to define any arbitrary combine operator that just satisfies some type properties here. And actually this might seem to be like a slight difference or a simple difference here, but it's actually kind of challenging to have a formal semantics for these different kind of combine operators here. So that was also confirmed in the TVM community, and I also just confirmed it. So it was really a lot of trouble to come up with a semantics that makes kind of sense for these operators here. Okay, so far we have just seen MDH's formal program representation here, so just from a formal perspective here. But Richard put a lot of effort over the last months and years in providing a full implementation of the MDH approach. And he is working on a Python-based compiler here. And here on the right side in the red highlighted box, you can see how matrix vector multiplication would actually be expressed in our Python-based user interface here. And the interface is actually designed to be very similar to the formal representation of MDH, so that any kind of formal reasoning that we have for our formal high-level representation here also applies to our DSL programs. And here we can see, for example, we also have these three higher-order functions kind of expressed in Python: out view, MDHOM, input view. Index functions are expressed, for example, via Python lambda functions. Then we have this multiplication here, just expressed as a mul instead of the symbol, instead of the star symbol. We have CC for concatenation, PW for pointwise computation, the scalar plus, and so on and so forth. And also the type parameter. So I think that's a very close interface. So it's very close to the formal representation of MDH here, which we consider as good. And yeah, the slide before I mentioned that multiplication function. So that's actually a pre-implemented function by us because multiplication is occurring for expressing many kinds of data per computations, particularly linear algebra routines and computations that are relevant for deep learning here. But we allow the user to use fully custom combined scalar functions here. So and actually, I would say they're kind of easy to implement. You just implement them in Python, maybe a little bit different because the input types are a little bit different. But here you can see, for example, how the multiplication would be explicitly implemented in Python. You just use the function and annotate it with a decorator here, and that's everything actually you need to do to have a custom scalar function here. And for a pointwise operator, we actually also allow using arbitrary kinds of binary operators here. So in the matrix vector multiplication example, we have used the scalar plus so to express the pointwise addition here. But that can be also, again, any kind of arbitrary user-defined function here. You just implement it in Python, use the decorator, and if all type properties are satisfied, that's completely fine then. And we actually allow even fully custom combined operators here, so even different from concatenation and pointwise. So these two can already express a bunch of different examples here. But if you want to have a new kind of combined operator here, so for example for prefix sum or something like this, it's actually also pre-implemented but different from concatenation and pointwise. But if you have something like this and that's not provided by us, you can also implement your own combined operator here. That might be a little bit more challenging. I would say if you get a little bit familiar with it, it's kind of okay, but it's a little bit more challenging than just implementing a scalar function or binary operator here. But at least this interface allows us MDH developers to come up with a kind of quickly with a new kind of combined operator if it's requested from any kind of user here. And yeah, it's also already mentioned at the beginning of the talk, we can also take straightforward sequential code as input. So for example, Python code. And that's actually how a Python code would look like if you want to optimize it via MDH. So you just implement matrix vector multiplication via these typical 2 for loops. And then again, just use the decorator where you say, okay, what's my input data, what's my output data. You explicitly state the combined operators here. And that's actually everything you need to do. And that's completely equivalent, again, to the formal representation, also to the Python-based implementation that we have seen on the slides before. And yeah, and that's actually what the two other guys that actually could not join us here today are working on implementing. So they are trying to bring the MDH approach into the MLIR framework here. And regarding the high-level interface, their work is actually done, and they could come up with an interface that's, again, completely equivalent to the formal representation of MDH. So the formal representation, the Python representation, and the MLIR representation are completely equivalent. And here, for example, you can also see again, so we have these 3 higher order functions, in view, MDHOM, out view. Index functions are, for example, expressed as affine maps, which are building blocks of MLIR. We have the type parameters and so on and so forth. And yeah, our MLIR interface has a particular advantage that allows easy integration of MDH into deep learning frameworks. So for example, what we are doing right now is, so from the MLR community, we already have a pipeline where we can lower TensorFlow and PyTorch programs to stable HLO. That's kind of, so they call it a dialect in MLR that can be considered as a kind of IR. This stable HLO is lowered to linalg. That's the representation that we have seen like 3 or 4 slides before. So it's actually already provided by the MLR community. And from this representation, this linalg representation, we can go now to the MDH representation and then generate the code according to MDH. So now regarding our low-level representation. So I have just one slide about the low-level representation so that you have at least seen it once. And the goal of our low-level representation is now to explicitly express in hardware and data optimized decomposition and recomposition of data pair computations. So how can we make the problem gradually smaller, that it fits into the memory and core hierarchy of modern parallel architectures, and how can we recompose these computed intermediate results back to the final results? So that's what the representation tries to express formally here. And yeah, the second major goal is the representation. We have designed it that it can be straightforwardly transformed to executable program code. So for example, in OpenMP, CUDA, and OpenCL. And straightforwardly in this context means that all the major optimization decisions regarding data movement and parallelization are already explicitly expressed in this representation here. And here on the bottom left, you can see how such an instance in our low-level representation looks like. So nobody is expected to understand this, but what actually happening here, speaking very easy and very technically, is we apply a multi-layered, multi-dimensional tiling approach. And for each tile, we say how it is assigned to the core hierarchy, how it's assigned to the memory hierarchy. So should tiles be computed in parallel? If in parallel on the GPU, for example, by blocks, warp, threads, and should these tiles be computed, for example, register memory, shared memory, device memory, and so on and so forth. These kinds of decisions are all expressed in this representation here. Okay, and we could also show, because of the design of our low-level representation, which tries to be very uniform and also try to follow some structure for all kinds of instances here, we could even visualize optimizations for different kinds of architectures and different kinds of computation in a uniform way, which is kind of this form. So here on the right side, for example, you can see here how the problem is made gradually smaller, in this case a matrix vector multiplication. At the bottom part, we compute on these smaller problems, and then we recompose these smaller results to the final result. Now regarding our lowering process from a high-level instance to a low-level instance, so this is actually based on formally defined performance-critical parameters. And our parameters don't aim to introduce some kind of new fancy optimization here, but they aim to unify, generalize, and combine, and also formalize well-proven optimizations, particularly regarding tiling, data movement, and parallelization here. And what these parameters actually determine is, so they kind of influence the shape of our low-level instances here. And actually they say mostly, so how do we want to exploit the core hierarchy? How do we want to exploit the memory hierarchy? When speaking very easily. And yeah, maybe not very surprisingly, we determine optimized values of these parameters, so optimized for a particular architecture and data characteristics using our ATF auto-tuning framework here. And yes, sure.
Yeah, I was wondering, since you brought up data movement, do you actually do prefetching of the data? Do you schedule data movement, occupying the freedom, utilizing the bandwidth that might be available at a certain point in time or something like that? Or is it just how much data has to transfer from main memory to secondary storage or something like that? Yeah.
No, so this, these parameters actually really express data movement. So they say we want to make a data movement here. So in the formal representation, they just say we want to make a data movement. And it depends on the backend how this data movement looks like, the copy operation. But we just say, for example, this tile should be in this memory. How it gets there, it's dependent on the backend.
So that can be instruction for the DMA engine or something
exactly,
like that.
Exactly, yeah,
Thanks.
exactly. Okay, and as a side note, so if there's some expert or ninja programmer that says, okay, I know how to determine maybe, for example, some of these parameters, or maybe even most, we optionally also provide a scheduling-based language that where an expert can express some or maybe even all optimization decisions, for example, to reduce the auto-tuning time, or maybe because she or he thinks I can come up with better optimization decision than an auto-tuning system here. That's actually a paper that we had on CC, so if that's kind of interest for you, you can check out the paper here. So now regarding experimental results. So we try to experimentally evaluate MDH in terms of all performance, portability, and also productivity. And for this, we try to compare against the best available solutions to us right now, which are, for example, from the class of scheduling-based approaches, Apache TVM, which works for GPU and CPU. It's a very well-performing and decent competitor, and yeah, it actually was even recently acquired by NVIDIA here. Then we compared to two polyhedral compilers, PPCG for GPU, Pluto for CPU. From the class of functional approaches, we compared to the lift approach, which works for GPU and CPU. And to make the experimenting really challenging for us, we also compared to domain-specific libraries provided by vendors, such as NVIDIA QBLAST, QDNN for NVIDIA GPUs, and Intel 1MKL and 1DNN for CPUs. And these libraries are particularly challenging for us because they're highly optimized for a particular domain and for a particular architecture, while MDH, and actually also other approaches that we compare to, are more flexible in these kind of decisions here. And yeah, we have 5 different case studies also that we have considered, and these are linear algebra routines, particularly matrix multiplication and matrix vector multiplication. We have compared. Used stencil computations, Jacobi computation, which is the 1D stencil example, Gaussian convolution, which is a 2D example. Then a case study from the domain of quantum chemistry, coupled cluster. We have this data mining example, probabilistic record linkage, and also deep learning case study. And actually the deep learning case study is again the most challenging for us because most of the competitors are highly optimized for deep learning computations, particularly the vendor libraries and also TVM. So our performance evaluation. Our performance evaluation is based on a runtime comparison, and here I have just one slide where I just present the highlights only for deep learning because deep learning is the most challenging, or was the most challenging case study for us. And what you can see here is the speed up of our approach as compared to the competitors here. So higher is better for us, and you're not expected to read all these tables here. So I have the summary on the right side. And for example, on the GPU, compared to TVM, we have speedups ranging from 0.88 to more than 2x. Compared to the polyhedral compilers, we have speedups sometimes by more than an order of magnitude. And even as compared to the hand-optimized libraries like QBLAST, QDNN, we have sometimes speedups of more than 2.5x. And similar things apply to the CPU. So they actually, compared to TVM, we have sometimes speedup of more than 3x, and also compared to 1MKL, 1DNN, sometimes speedups even more than 9x here. And here keep in mind, so deep learning was actually even the most challenging study for us. And for other computations, like for example, just a straightforward dot product, as compared to TVM, we have a speed up of more than 170x, for example, most likely because dot products are not that much occurring in deep learning. The portability evaluation in our paper is based on the Pennycook matrix. So it might be not very obvious how to measure portability, but John Pennycook came up with this Pennycook matrix, which somehow can assess portability here. Without diving into too much detail, but a value close to 0 means low portability, a value close to 1 means high portability. And for the deep learning case study, for example, we could achieve speedups. We could achieve higher portability than TVM actually in all cases. And even actually also as compared to the other competitors here, which actually just achieves the lowest speedup of 0 only, mainly because they are bound to a particular architecture here, and thus they are not functional portable, and thus especially also not performance portable. And the product evaluation of our paper is based on intuitive argumentation actually, because classical code metrics like lines of code or development effort are not very meaningful for these short and concise programs as used by MDH and also the competitors here. Now regarding work in progress, results and future direction. So we think that's just a starting point, this MDH approach, and I think we have a lot of ideas for many interesting future directions that are kind of promising. So for example, particularly regarding expressing fusion-based optimization, so we think we can exploit algebraic information that are captured in our representation to express very aggressive fusion optimization on the high abstraction level and also the low abstraction level here. Then we have some ideas of how we can very structuredly target domain-specific hardware extension like tensor cores, for example, and also sparse computations, and actually many more. And yeah, that actually brings me to the summary about MDH. So I'll make it quick. So MDH's 3 key goals are to achieve performance, portability, and productivity in one combined approach. And for this, MDH formally introduces program representation on both the high level and also the low level. The goal of the high level was to express data per computations uniformly, fully agnostic of optimization and hardware details, while still capturing all the information that are relevant for generating high-performing code. And in contrast to the high-level representation, the goal was to now explicitly express and hardware and data optimize decomposition and recomposition of computations so that we can efficiently target the memory and core hierarchies of modern parallel architectures here. And MDH also introduced a lowering process so that the high-level instance in our high-level representation can be fully automatically lowered to a device and data-optimized instance in our low-level representation based on auto-tuning. And yeah, in our experiments, we could confirm that MDH often achieves higher performance, portability, and/or productivity than popular state-of-practice approaches, also including hand-optimized libraries provided by vendors. I think the most interesting point here is there are a lot of many interesting, promising future directions that we can hopefully present at some array event in the future. And okay, just one last note about MDH. So that was, of course, a very quick informal dive in just regarding the high-level representation of MDH. So if that could somehow gain your interest, we have a paper about that, the archive version particularly, which is a long version of the top plus version, where you can find all formal details about all the stuff, the high-level representation, the low-level representation, the lowering process, and so on and so forth. And there are also a bunch of further experimental results provided. Okay, now kind of quickly regarding ATF. So again, regarding ATF, we have a website about that. So if that somehow can gain your interest, please feel free to check the website. And we consider the paper from TACO from 2021, that's the main ATF paper here. So what is ATF? So ATF is first of all a framework or a tool that finds the values of performance critical parameters as we have seen for MDH, so like tile sizes, number of threads, but actually also these parameters can be arbitrarily complex. But actually a lot of approaches doing this, and the major goal or the major contribution of ATF is that it allows these kind of parameters to have so-called interdependencies between them by having the notion of constraints. So for example, that's particularly important when you target modern architectures like GPUs where you have hierarchies of memories and where you have different tile sizes on different layers. And of course the tile size on the lower layer needs to be chunked out of an upper layer tile, and that's something that you can express, for example, in ATF. And to efficiently handle these interdependencies among these kind of constraint parameters, ATF introduces novel processes to generating, storing, and exploring the spaces of these kind of parameters here. And that's actually based on two major contributions here. So ATF comes up with a new notion of constraints. So we define constraints on parameters rather than the search space. And we also introduce a new kind of search space representation that's particularly optimized for these kind of constraint parameters here. Maybe more interesting for us is how is ATF used and how can it be used here. So to use ATF, we have different kinds of interfaces, but I think the Python interface that Richard implemented and presented this year at the CC conference is the most interesting one. So to use ATF, you just implement a simple Python program. I would say it's simple. So because you just need to, so you just specify the parameters by their name, possible range, and constraints. The constraints can be any arbitrary lambda function here, for example, that may contain other kinds of tuning parameters here to express these interdependencies between parameters. Then you can implement your cost function, so the function whose cost needs to be minimized, for example, the runtime or the energy consumption, arbitrary in Python, so it can be any arbitrary Python function that takes a configuration as input and returns the cost. And we actually also provide pre-implemented cost functions for users' convenience. Yes, please?
How do you come up with these cost functions? Where do these cost functions come from?
So these cost functions are provided by the user because we don't know what kind of program you are tuning. You just need to specify a Python function where you kind of execute, which the function takes the configuration as input, so a particular choice of the parameters that you want to tune. And for this particular choice of parameters, you need to tell us what your program has a cost for example, by executing it and report the runtime to us. And that's how we use this function as a black box connection to your program, and that's how we optimize your program here. And then we say at the end, okay, this configuration led to the lowest cost. That's how it works.
So that means if you want to run your autotuner effectively, you have to essentially run bits of your code in different configurations on beforehand.
Either this or you come up with an analytical cost model or something like that. You just need to somehow tell us the cost of your program, and how you do that is up to you. So we actually run the program. So right now we don't have a cost model yet, but that's how we can keep this framework very generic. So that's also why it works for actually any kind of program. You just need to, that was the important point for us. Yes, please?
So for the benchmarks that I gave before, I assume you were using ATF.
Exactly, yeah.
And how did you use, what cost function did you use there?
That was, for example, for the GPU example, there was a CUDA cost function that we have implemented ourselves. So the kernel was kind of executed in this function, and then we have reported the cost to the runtime as cost there. So a Python function we really call a CUDA kernel that we have generated according to MDH. put the parameters in it so that the CUDA kernel was customized with the particular tile sizes, numbers of threads, and so on and so forth. And we have run it, measured the runtime of it using the CUDA API, and then reported the cost. And that's how we did the auto tuning there.
Thank you.
Okay, so yeah. And actually for CUDA and OpenCell, we also provide pre-implemented cost functions that you don't have to implement all this kind of host code where you issue the data transfers, need to compile the OpenCell or CUDA kernel, for example. And yeah, they're also kind of convenient to use. So in this example, for example, you can see even the pre-implemented CUDA cost function from us here. For example, you can see you just put the kernel code as a string into our cost function and you say which GPU you want to target. In this case, the one with the device ID 0. What are your arguments? What is the grid dimension, the block dimension, and everything you need to do for the cost function in this case here. And then we generate the host code for you and execute the kernel, measure the time, and so on and so forth. But if you, for example, come with a Java programmer, whatever, so you need to implement your own cost function. And yeah, ATF actually also provides various pre-implemented search techniques and abort conditions. So we have a bunch of different search techniques from numerical optimization. And we actually also have meta techniques because meta techniques are, actually you have one meta technique that chooses automatically a search technique for you from our pre-implemented ones. So that's highly inspired by the OpenTuner framework from MIT here. And yeah, that's also kind of convenient to use there. And we also come up with a bunch of different abort conditions. So they tell when to stop the auto-tuning process. For example, based on the tuning time, based on the tuning results, or maybe as a compromise of both. So for example, you can say to ATF, okay, if within the last 2 hours you couldn't improve the result, just stop, and something like that. Okay. Yeah, that actually also already brings me to the summary about ATF here. So the major goal of ATF was to support parameters with interdependencies between them, and for this it has introduced novel process to generating, storing, and exploring the spaces of these parameters, because these interdependencies make things much more complex than in the easy case where you don't have interdependencies. But ATF actually has a bunch of further features that I could not present on the slides for brevity here. So for example, we put a lot of effort in providing a very productive user interface here, and in our papers we actually also argue that it is simpler to use than the interfaces of other approaches, even when you don't have interdependencies between your tuning parameters here. Then, as already mentioned, we have different kinds of search techniques and abort conditions, and the framework is actually extensible in both points here, so the user can also come up with its own search techniques and abort conditions. For this, for example, she or he just needs to implement a simple Python interface. And actually, ATF provides different kinds of interfaces here. So the ATF concepts, we have implemented them in Python. That's what I've presented on the slide before, but we have also C++ interface. For example, when you want to auto-tune C++ programs at runtime. Then we have also domain-specific language, which is very easy to use, very convenient to use when you want to auto-tune just at compile time and not at runtime. And the ATF concepts actually could be integrated in any kind of general-purpose language here. So also Java, if you want to auto-tune Java programs at runtime, and so on and so forth. But we don't have a Java interface yet. And yeah, that's actually the end of the talk. So thanks very much for attending and listening. And I think we should have plenty of time for questions now. Perfect. Thanks.
So this is the keyword, plenty of time for questions.
Yes, please.
Where are the questions? There.
So I'm wondering about the ATF side of things. Okay. And so I guess you're sort of saying that you sort of like black box optimization methods for a cost function. So then so what sort of exploration, how do you explore the sort of search space? Like, is it that you have rewrites defined for the low-level MDH representation, or like what sort of approach do you use there?
So we represent the configuration, some kind of coordinate space, and then we have numerical optimization techniques to explore this coordinate space here, like for example hill climber, simulated annealing, and these kind of search techniques. That's how the exploration works.
Yes, but for instance, for simulated annealing, there's like some that you start from, you have some current configuration, and then you have the neighboring configurations. So exactly. What sort of neighboring configurations do you have? Like
Okay,
which ones do you?
I think your question goes more into the direction how the search space represented, and that's kind of this structure here that you can see on the bottom right here. We have a tree-like representation of the search space here, and what we are doing, we are mapping this tree on a coordinate space, and the coordinate space actually, it has as many dimensions as you have layers in the tree, and then the values in the coordinate space are between 0 and 1, and then you say, that's how you can navigate through the tree. So for example, the first dimension of the coordinate space is mapped to the first layer in the tree, the second dimension of the coordinate space to the second layer, and that's how we kind of roughly map the coordinate space to the tree, and that reduces the challenge of exploring this tree to exploring a coordinate space, which actually is the most efficient structure for most of the search techniques that we have in numerical optimization.
Okay. So you also have like a generic representation of the search space.
Exactly.
Okay, yeah, and so that is also interesting to know. I did miss that, so that's my bad. But I don't. And how do you construct the search space? Like, what sort of so you operate on the low level MDH representation at this point, right? Or something different?
So the MDH search space would be represented as such kind of a tree.
Yeah. Okay.
Is that what you meant? So we have different kinds of parameters. Each parameter is represented here as one layer in the tree. So when you have like 10 parameters, you have a 10-layer tree. So
what sort of parameter was it? Could it be, for instance? Could you
a tile size, for example.
Okay.
A tile size, for example. Numbers of threads. And exploiting fast memory resources yet or not. We have Boolean parameters also in it. So it's actually this. Where is it? This table here.
Oh, I see. Okay.
That's of course a very mathematical presentation, but these are, for example, these are numbers of so these are tile sizes here. For example, that's a loop. Technically that's kind of a loop order. There's a permutation parameter. Then let's skip this one. But here's the memory regions. For example, tiles should be they computed in which memory region: global memory, register memory, shared memory when you target GPUs, and these kind of things.
So the lowering process itself.
It's generic in these parameters.
Okay,
so exactly.
Okay, that's interesting. Okay, thank you. Now that's a lot clearer. Thank you.
Okay, cool.
More questions?
I was wondering, in what sense do you use the word homomorphism? Is it there are a lot of operations that have a certain homomorphism?
That's actually a very good question, because I don't even have to bring the definition of homomorphisms here. So the function that we can express via our higher order functions, so with this kind of representation, need to be homomorphism. So homomorphism actually means that you can split the iteration space in any dimension, when speaking very technically, and then you have an operator, when you, for example, have split the iteration in some, that you can compute independently on these two parts and then combine it together. In any multi-dimension means that any loop, for example, of the iteration space, in a more imperative setting speaking, can be split and you can combine the results here. That's these homomorphic properties here. When you have the input, you put it in two parts, compute on this part, and then you can combine it together, and the input can be split in any dimension of the iteration space here. That's actually what I meant. We have defined formally data parallelism. It's not on the slides here, but in the paper that's described so what exactly the target class of computations for us, and all these computations can be expressed exactly with these kind of expressions there at the top. Yes, Sven, please.
Does it work now? Yeah. Yeah, thank you very much. Very exciting. This slide is actually perfect for my question.
Okay.
So I see lots of indices here, and I know that Python is not exactly very strongly typed. And how do you know that my arrays have sufficiently enough elements? And I assume that all your homomorphic transformations are fine, provided that I don't have out of array accesses.
So that's where we check that in the Python interface.
Well, generally, how do you make sure that you
have the iteration space size that's explicit. So we are setting in the iteration space size. We have this I and k. Then we can check via the index. I think so. What we actually do with these I and k are concrete values when we have, so they're statically known. And then we know based on the index functions how large these matrix and the vector, for example, must be, and then we just check that.
What if you don't know them statically?
Currently, you assume them statically. If you don't know them, so in our formalism, that would be some kind of undefined value. So it's not implemented yet. So in the implementation, they always need to be statically available, right?
And even if you do know them, how do you make sure that your matrices have enough elements? That actually the shapes of the matrices are matching your iteration spaces.
So for a fine index function, it's, I think, kind of easy. You just replace some kind of the lowest and the highest value and check if it's some kind in the middle there. And if you have not a fine index function, so the easiest way would be to just test all values there.
But there it just says M is buffer T. How do I know that M is of sufficient range?
So when you take...
Oh, you have down there you index M by IK, right?
Exactly.
And how do you know that the range, capital I, matches the dimensionality of M?
I'm not sure if I got the question, but I think Richard got it.
I think what you mean is when we actually run it, we pass NumPy arrays, and they have the shape inside of them, so we can check if the shape of the NumPy array matches the inferred size what Ari was talking about. So
if what we're getting, what we're expecting is kind of the same. So we can compute what we're expecting based on the static information that we have here. And what the user provides is kind of captured the NumPy array representation you meant. And then we can just check if that's...
Yeah, but can you check this statically?
I think so.
I mean, not statically, but at runtime of the Python program.
At the runtime of the Python program, but at the compile time...
So if it doesn't match, then you get an error.
Right.
But Python is sort of the meta language, right? It's just sort of setting up the program before execution and compiling it. So this
exactly.
Like Python isn't statically typed, but this is just the host language. Like it
Yes.
it is doing the typing on that sort of phase.
Yeah, but if you... Yeah, okay. Yeah, thank you.
Thank you, Richard.
Thank you. More questions?
There's one more. There's no other one because this is a technical detail. This is actually about the Python interface. I'm just wondering, the body of mth-matvec is the AST of that parsed? Are you literally executing that loop? Is there a point to executing it in that way, or is it that you're parsing the AST and looking at what the code is and then doing something else with it?
Parsing the AST.
Okay, it's a little sad, but I'll take it.
Anything else? Okay, so while you think about some other question, I have one myself. First of all, just a quick one. I assume auto-tuning is the key to your good performance compared to the other approaches. Is that fair to say?
Particularly compared to the vendor library, because the vendor library is only compared...
Of course, they can't do this. I mean,
exactly, so they are kind of optimized to what average high performance, particularly over data characteristic, and compared to them, I think our performance advantage is mainly because of the auto-tuning. I cannot tell you with certainty because the libraries are closed source, but most likely it's that. Compared to TVM and the other approaches might be different things because they're also involving auto-tuning, but particularly compared to QBLAS, QDNN, 1MKL, 1DNN, I highly assume that it's because of the auto-tuning, because we can specifically auto-tune also for the data shapes and sizes, while QBLAS and QDNN are just optimized for the architecture, but not specifically for the data sizes. I think they have kernels that are optimized towards a range of data sizes there.
One other question to the other side of your work. You call MDH a high-level representation, and I wonder what's the difference between a high-level representation and a programming language?
You can consider it as a programming language, but high-level representation means high-level in the MDH stack, kind of. So we have.
Yeah, I understand that, but the question is: so is that, or the excerpt of Python code that we see here, is that the way you expect things to be programmed?
Exactly. So maybe in the best case, in this way.
Mm-hmm. So it's basically a true.
Exactly, yeah. So
one-to-one translation into Python, yeah.
Exactly, yeah.
Okay.
And the top part is a formal representation of that program there.
So you don't consider this to be, at least not at first, to be, let's say, a compilation target from something else, because that could be.
Of course, that could be. So we can.
But it's not your goal.
Not our goal, but being a backend for other approaches that operate on a higher level, of course, that would be very interesting for us. So we operate at this level, and yeah, that makes fully sense that it's a backend for other kind of approaches operating at higher levels there.
Okay. Then, while you still think about more questions, my last one from me. On slide 17, you had these buffers, at least that's what I noted down, Is this slide 17? Are there buffers? Yeah, there are buffers. So you expect that there are explicit buffers that you get in, or could these be kind of shared pointers in reality? Or do I have to copy everything into dedicated buffers before and copy it out after?
I think in this case we just say that these are just type hints, right?
Type hints here, but to your question, you can pass any NumPy array as inputs for these expressions, and of course these NumPy arrays can also be used in other computations. Is that what you mean with shared pointers? Or?
Yeah, I think so. Yeah, okay. Yeah. So it's not a dedicated buffer. It's just let's say a reference to a buffer that is somewhere.
Right. Yeah.
And the writing buffer.
But here in the decorator, these are type hints, right? That are not the actual buffers. The actual buffers are not in this code example.
Right. Technically, these are not type hints, but yeah, that are not the actual buffers. That are just the descriptions of the buffer type.
Oh, I see.
Okay, so not Python type hint, but the type information. So that's what I meant. And the actual buffers are not in this example. So that's just the code that we need to generate the kernel. And this for this generated kernel that we cannot see on the slide, there we put in the concrete buffers, right?
Right.
Right, then I use also the word right, and I don't see any other questions, so I would say let's thank Ari and Richard again.
Thank you.
And that concludes our afternoon session, and we have a generous coffee break until 3:40, if I read the program correctly. And then we reconvene for, well, I think two more talks in the panel. Thank you.
Yeah, hi, welcome to the last session. We have two amazing papers. The first will be given by Guido Martinez, who works for MSR, research engineer. So Guido, take it away.
All right, thank you. Yeah, this works, perfect. Yeah, so I'm going to tell you a bit about Kuiper, which is a language we're developing for doing safe, first of all, GPU programming, and also verifiable in the sense that you can prove that it's doing what it has to do, and also not relinquishing efficiency. And this is joint work with a bunch of people. A special shout out to Jonas, who was our intern last year. So the first question, of course, is why? Why do we want a language that's verified GPU programming? And the first and main reason is that GPUs are really hard, which is probably not surprising to this crowd. There's two different memories. You need to deal with this weird parallelism with the blocks and threads. You have barriers and asynchrony and memory hierarchies, and errors are kind of may go unnoticed at sometimes, and debugging is also hard. So it's like not a great place to be as a programmer. And performance is also like paramount. It's like pretty much. If you're using GPUs, you probably really do care much about performance, and we don't want to renounce full performance or have any kind of dynamic checks or sacrifice not be able to do what we want to do just because we have to avoid bugs and be safe. And we want very precise choice of like the memory layout and when we copy stuff and etc. So there's kind of this trade-off between safety and a correct program, and also being like 100% performance when you're developing at scale. So verification is kind of a way to get rid of that trade-off and do not trade performance for safety. You can do anything you want to do, use any fancy instruction or a pattern or whatever that you want to, as long as you just prove it that it's safe. So Kuiper is a language that starts with this mindset. It allows you to do many things. So it supports all of the usual suspects of GPU features. So there's heterogeneous memory, there's sharing between different threads, parallelism, asynchrony, and it's always memory safe and data erase free by construction. Optionally, you can even verify that your programs are doing what you want them to do. So if you write a fancy gem that's splitting the thing into 3 levels of tiles and sharing between different blocks and whatever, you can anyway at the end prove that it's actually just computing a gem at the mathematical level, and you don't need to trust the implementation. You just need to look at the specification. And there's few restrictions. You can write the fancy algorithm that you want, as long as you just prove it that it's safe. So far, Kuiper is relatively new. It's maybe like a year-ish old. We have like several flavors of gems, like fancy matrix multiplications, with no performance hit compared to a handwritten implementation. We also have programs using atomics. We have a parallel reduction implemented. We can do asynchronicity, like launching kernels asynchronously, use floating points, and do some forms of genetic programming, so like a very free style of polymorphism. Kuiper is built on top of F-star and Pulse. F-star you might know as this proof-oriented verification language. Pulse you might not know about, but you're kind of in luck because in Friday we have a paper about it on PLDI, so if you're curious, you can show up and listen to it. I'm going to show you a bit of Pulse today, but just kind of like the basics to get us going. Pulse is a language that's based on concurrent separation logic. That might sound a bit scary. I'm just going to give you like a primer in 1 minute of what this is about. So it's an extension to Hoare logic, so pre and post conditions, that makes reasoning about pointers and data more compositional. So the pre and post conditions in separation logic represent resources which can be spent. They're not just about truth. And threads own resources. So these are like the prototypes for simple functions like allocate a reference and free it. Allocate, in this case, I give it an initial value and it gives me back a reference. And as a post condition, it says R points to B. And this is, in a way, telling me that R does point to B in the thread, in the heap, but also that I own this fact. I am the single owner of this fact that R points to B. And then I can free it. So this other function free here has as a precondition that R points to B. And then when I call it, I give this precondition, I give this resource, and what I get back in the post condition is empty. I lose it. Once I free a reference, it's no longer there and I cannot use it. And then some resources like this one can be fractioned and shared. Fractioning means, for instance, if I have a reference that points to a value V, I can fraction this resource into 2 resources saying that R points to V, but I only know half of this and I only know another half of this. And then I can give this other half to another thread. And to read a reference, I only need a fraction of a permission. I don't need to be the single owner to read. So this is the way that concurrent read-only accesses are permitted in separation logic. So this frac notation is what represents a fractional resource. And then, for instance, this last thing is copying y into x. I only need some read permission over y. And then my precondition is that x points to some value x0. And my postcondition is that now it points to something different because I'm changing it. And I am the single owner. If it doesn't say, hey, frac, I'm the single owner of this resource. Yeah, so for instance, once you have this language set up, this is like a very tiny pulse example. If I allocate a reference 1, r, they initialize to 1, I get the fact that r points to 1. I could free it, and then I lose this fact. And if I try to do anything with r after it, this fails. Like I don't own this resource anymore, and this is gone. So look into Pulse if you're curious, or ask me about it at any point. So how does this help us in GPU programming? So I'm going to show you a very simple example of verifying a kernel thread. So this is an example of a kernel that takes 2 arrays in memory and pointwise multiplies them into a separate array, AR. So this is what I'm showing on the right here is actual Kuiper code. It has 3 parameters, A1, A2, AR, that are GPU arrays. This is a parameter about that is the thread ID of the thread that it's running. This is similar to thread ID, thread index.x in CUDA, but we make it an explicit parameter because it looks nicer. And the implementation inside the braces here, the body, is really just what you would expect. I read array A1 at TID, I read array A2 at TID, multiply the values and save them into AR. Now, the implementation is direct. What about the specifications? So we need to add some stuff. So first of all, we need to say this function, when it's called, owns some fraction of the array A1 and some fraction of the array A2. So it is allowed to read them. If I did not own this, I cannot read them at all because they could be owned by some other thread who might free them, so they would be unsafe. When I say preserves, it means something that is required and also given back at the end. So we take some permission on A1 and A2, we give it back at the end. And the requires, another part of the precondition is that we know and we own that the TID cell of the result array points to something. And in the postcondition, we say we change this V0 value, and now it points to something else, which allows us to write over this thing. And this one is full permission over the cell. So this is like the separation logic specification that you would expect for this function. In Kuiper, we need to add a few more things to make this actually into a GPU kernel, basically. We need to mark this function as a GPU kernel. This thing is kind of a token resource that we use just to mark that this thing will run on the GPU, and it can be spawned into a thread group, and it can use GPU-only operations, like barriers to synchronize and etc. Another thing is that we need to explicitly encode the grid constraints. So if I'm saying that this function will multiply 2 arrays of size len, this needs to run in a block of size len. I cannot just run whatever number of threads I want. If I want this postcondition at the end that they actually multiply to 2 arrays, we need the block to be the proper size. So this is encoded in the specification as well here. And then when we're verifying and trying to get decent, reasonable properties out of this, we need to add some proof steps once in a while. So in this case, if we want to verify that at the end we get the pointwise multiplication of these 2 sequences, there's some convincing that we need to call to do to get Pulse to accept this. So it's those final 2 lines. But if we only care about safety and we just want a program that we know will not crash and will not have data races, this can be removed just by weakening the specification and saying AR_TID points to some other value, some new value. So how do we execute these things? So I'm showing you this fancy language that looks kind of different from CUDA or something, and it has the specifications. The way we execute these functions is by extracting them into CUDA-C. So after we check these functions in Pulse, or in Kuiper, we extract them and we get code that looks exactly like this, actually. So it's pretty much what you would expect. The code is somewhat readable. All of the specifications and proofs are gone. You just get plain CUDA-C code out of it without any kinds of dynamic checks. We don't do any kind of transformation in that sense. And this can be used directly by CUDA clients. You don't need to buy into to write your entire program in Kuiper to be able to use it. Does it kind of make sense so far? Good. So I was just showing you how to verify one single thread in a way. This is the function that executes one single thread. When you want to spawn a kernel, we have some big resource, like I have 2 of my input matrices AB, and I want to write the product into a matrix C. So I need to split these resources and to be able to spawn a big kernel and allow them to compute. So the way this looks like in separation logic is roughly that At the beginning, as the main thread of my function, let's say, of my program, and this is just a CPU thread, I fully own A and B, and I fully own C. And the first step I will do is split these resources in some interesting way. So for instance, let's say I'm going to spawn, let's say 16 threads, but they don't fit on the slide, so I'm just going to show you 4. I'm going to spawn a bunch of threads, and I want every thread to be able to read from A and B and to write into a single cell of C. So the steps you need to do is take the matrices A and B and share them across all of the threads, so in 16 equal pieces, and everyone gets some fraction of permission. And the output matrix, it's a different kind of sharing. We explode it into cells and give to every thread full ownership of a single cell, so they can mutate it, but they can do nothing else with the rest, not even read them. After we do this, you can spawn a big kernel that works. Every thread works on one of these output cells. They modify them somehow. Now they make them purple. They cannot really modify the inputs because they all share them. So sharing the modifying them when someone else can read them is a data race. And then at the end, we'll also join all these resources and get back, full permission over AB and full permission over the now modified C. And I should say, all of the computation really happens in this middle step. Here, when I say all of this stuff, sharing resources and slicing the matrix and all this, these are all ghost steps that don't have any computational meaning. They're just convince, they're just proof artifacts in a way. So with that in mind, the way we model kernel launches in Kuiper is, if we consider launching n threads, let's say we have a simple example of, let's launch one block of n threads, and that's it. And every thread I, the thread index I, has a precondition pre-I and a postcondition post-I. So if we want to launch all of these threads in parallel, what we have to do is provide at the beginning each of the preconditions of the threads separately. We need to be able to split split our resources into separate compartments where each thread has its own preconditions separately from the others. Then we can run all the threads in parallel, and we get back all the postconditions separately. Now this is generic enough, but it's in a shape that's not really useful. So the pre and post conditions of the full thing have a simpler way of, usually have a simpler way of expressing them. So we add some ghost steps to tweak it. So the kernel specification looks most like there is a big precondition and a big postcondition, and then there is a way to split the big precondition into the individual preconditions, run the threads in parallel, you get the separated postconditions, and then you put them all back together into post. So at the end, this looks more like, okay, you give me permission over the full matrix, and I'll give you back permission over the full matrix at the end. Even though in the middle, it's all shared in this slicing and sharing and this kind of interesting patterns. And here, this was an example of just one block of n threads. Usually, a grid is, at least has 2 levels, so you have to spawn blocks, and each block spawns a number of threads. So the same idea applies, just recursively. You do this 2 steps in a row. And it allows you to capture the specifications of more complicated grids. So once we have this kind of proof done, we can package it into what we call a kernel description, which means that, so there is a type in Pulse called k-description that says, this is a package of a kernel that goes from pre to post, and it does so by calling some kernel function, and it has some grid size, and here are the proofs that, that show that this is all correct. And once we define an element of this type, we can forget about all the details of the kernel. This is all irrelevant, basically. And since they encode the grid size and all of that, we can just spawn a kernel description. And the function that spawns a kernel looks something like this. Give me a kernel description that goes from pre to post, and I require pre, and I ensure post, and that's it. And then everything else is happening under the covers. And there's no messing up, when you spawn a kernel, there's no messing up the number of blocks and threads and et cetera, which can happen in CUDA. This is all encoded in the record. Does this make sense so far? So another of Kuiper features is that going beyond like the safety and the way the separation logic is involved is that we make heavy use of polymorphism and specialization. So Kuiper inherits polymorphism and type classes from Pulse and F-star, which we built up on top of. So in this example here, this is a type of a matrix multiplication. It's polymorphic over the element type of the matrix, so the type of every cell, as long as that type is scalar. This is a type class constraint in F-star. The type being scalar just means that it has a plus and a product, and a 0 and a 1. And the implementation here is completely parametric over the type we're working on. And when you choose a type, you can specialize this and generate specialized CUDA code that works over the particular type without any runtime, like dynamic dispatch or anything like it. You can also use this, for instance, if you want to compute shortest distances in a graph, you can instantiate this with the min and plus semi-ring, as Amir was telling us this morning. And this allows you to just reuse your matrix multiplication and specialize it to compute shortest distances in a graph at no cost. Right. Going a bit further than this, actually, we can write programs that are not only polymorphic over the type they work on and the operations they work on, but also on the matrix layout. So I keep saying we have these matrices that are in memory some way. There's many representations you can use for matrices. The two most basic ones are like row major and column major. So ideally, I would like to write my algorithms just once and then just instantiate them for different layouts. And Kuiper supports this in a very comfortable way. So in the type you see here on the right, it's saying this function takes three matrices, GA, GB, GC, and they have some layout, LA, LB, and LC, and this is defined in some way in F star. And there is a type constraint saying the layouts have to be concretizable and computable. And the layout, the only thing that the layout is defining is where does the cell ij of the matrix go in memory. And if it's row major, it's I times columns plus j, and if it's column major, it's the dual. And this layout doesn't even have to be regular. If it's a fixed size, like any crazy bijection works. If you're working over matrices of 4x4 and you decided that you want to store them by rows, but some row is backwards or whatever, this can all be modeled in Kuiper. And every function we wrote is genetic on top of this. And specialized implementation is also possible. So we're currently looking at trying to model tensor cores inside Kuiper, and we will definitely need to have specialized. They use a given particular representation, so those are not polymorphic in a way. So all of these algorithms, we write them in this very polymorphic and specializable way. And once you do this, you can specialize a given function. So for instance, here's this mathmul GPU function here is a very polymorphic matrix multiplication, and there's a specialization function that says, okay, specialize it now to floats, and the two inputs are in column major, and the output is in row major. And out comes this code, which is kind of reasonable CUDA for this. And if you look closely, you will see that the array accesses to GA and GB happen in column major, and that the access to the output GC happens in row major. But I didn't have to think about any of this when I wrote this. We just verified this once, and we also verified what column major and row major mean only once, and then we get to specialize every combination of these functions. So we're getting this specialized verified kernels for free with the same guarantees, and there's no runtime hit. This CUDA code is exactly what you would expect. And any parameter is specializable. So I've been telling you about the type and the operations and the layout. Another important parameter here that you can specialize is a tile size. So you can define many versions of matrix multiplication that copy tiles into shared memory and do this a couple times. And the tile size is a very important parameter. So what you do in Kuiper usually is you define a function that does this where the tile size is just an argument, so a dynamic argument. And you verify this function. And then you can choose to specialize it to 2, 4, 8, 16, 32. And then you tune it to see which one works best. And it's easier to tune in a way. This allows you to tune more easily, since you know every version is correct. They are all correct by the fact that you verify the genetic one. Just a minor fact, we also support some basic forms of rotation fusion. So if let's say you need to compute the product of A and B, A times B transposed, well, what you can do is compute A times B, let's say they're in row major, you do the product into column major representation into some buffer, and then if you just flip your view, this is really the transpose in row major. So this can all be proven inside the tool, so you can avoid like spurious steps of transposing and etc. Today, by the way, with this specialization trick, we're generating around 15,000 lines of CUDA from around 15,000 lines of F star, or Pulse or Kuiper. This ratio is usually much lower, but the exponential verification here really kind of gives us an edge. Some more fancy features that we support as well are barriers. So in a block, you usually need to synchronize between the threads, and so the way a barrier works in CUDA is all of the threads have to reach a barrier before they can all go. and this allows you to make sure that some things have been copied or whatever you're doing. The way we model this in Kuiper and in separation logic is that barriers have a precondition P that the threads have to provide. So from 0 to n-1, let's say there are n threads, each thread has to give P of 0, P of 1, P of 2. So thread I has to give P of I into the barrier. And then when they all get there, we model that there is some ghost shuffling of resources that happens. And every thread comes out of the barrier owning Q of I. So thread 0 gave P of 0 and gets Q of 0, and the same for every other resource. And the only proof a user needs to do to show that a barrier is correct is that this is actually a shuffle, that if you take all of the P's, you can turn them into all of the Q's. This is useful, for instance, if you're using a local cache, like if you're copying global memory into shared memory, which all of the threads in a block share. You use them to say, at the beginning of the iteration, every thread in my block owns a single cell of this array. So the barrier, the precondition of the barrier is that I own a given cell of the array. And the postcondition of the barrier is that I own the full matrix with just some fraction. So then what happens when you call sync threads is that after this, every thread owns a fraction of the matrix. And then you can also go back with the same barrier to the previous state and keep copying memory back and forth and sharing them between all the blocks in the threads, all the threads in the block. Sorry. Another a bit more fancy feature that Kuiper supports is asynchronous kernel launches. So usually, in CUDA, launching a kernel does not immediately wait for it. It's just launched and scheduled into the GPU to be executed, and you can spawn many of them at once. We also model this in Kuiper and allow you to reason about this stuff. So the way this works is we use a reasoning principle for this kind of stuff called pledges. You can see our PLDI paper on Friday for a deeper explanation of it. But a pledge is kind of like a coupon that tells you what will happen in the future and how you can get it. So the key reasoning principle of a pledge, it looks kind of like an implication. A pledge says that if I own P, and I also have a pledge that whenever P holds, you get Q. So pledge PQ, you should read it as kind of a coupon that tells you that you can cash it in. So then when P holds, you get to keep P and also obtain the postcondition Q. And the way we model this asynchronous launches is that if I want to launch a kernel that has some precondition pre, I need to give the precondition so the thread can execute. And then what I get at the end is the most important bit is this pledge that tells me when the current epoch is done, which I'll tell you about, but that is in a minute, then you'll get the post, but you don't get it immediately. And the way you get that the epoch is done is by calling sync device. And sync device basically advances this epoch counter and tells you like, okay, the current epoch is now done. You've waited for it. So then you get to call redeem pledge repeatedly over every block, every kernel you spawn to get all the post conditions. Yeah, so that's about what I wanted to tell you. Kuiper is this framework for writing genetic verified kernels at zero cost. So far, we don't want to compromise on performance. So everything we're doing, we're generating very first-order CUDA code and checking that it's actually at the performance we expect. We cover a decent chunk of CUDA, so different grids, shared memory, barriers, atomics, floating points with many precisions, asynchrony. We can also prove some stuff about floating point computations, but I didn't have time to go into that, but ask me if you're curious. We verified several building blocks already, many flavors of matrix multiplications. We have a parallel reduction using barriers, another parallel reduction using atomics across blocks, and asynchronous invocations, and etc. By the way, this table right here is for many different implementations of matrix multiplication. The ones that are not in bold font are just handwritten that we, just normal CUDA code, getting closer to kubeless-like performance. The best one we've done in Kuiper is this 1D block tiling, and we actually beat the performance of the original CUDA code that we were mimicking. For the others, we're pretty much exactly the same because the CUDA code is really exactly what you would expect. And we plan to keep going forward. The things we now need to make a bigger dent in this, to get closer to 100% is like warp level operations and tensor cores and etc. Yeah, so I'm going to do a shameless self-plug. So after this session, I'm going to be at the Microsoft booth. I'm going to give a demo of this stuff. So if anyone is interested, you should feel free to come and chat. And yeah, I'm happy to take any questions. So thank you.
Thank you. Questions?
Cool. Thanks for the talk. So one question I was going to have is, have you guys looked at, so like Cutlass and Qt have built a bunch of abstractions that actually have good semantics, I think, for doing this kind of thing, where, for example, like Cutlass exposes an atom, which is like a MMA atom, and everything is defined in terms of these layouts that are algebraic. And so you could actually define them, I think, where the precondition, postcondition would sort of have like an if statement and it effectively like what level of the hierarchy you're doing, but they're modeling copying from shared memory to global and back to registers. But I think it actually would be a good abstraction to think about because they've sort of done some of the modeling, and then the layouts that they have are more general, and that you can use them to cover not only the modes of that you have here with like column, row, major, et cetera, but like complicated tilings and shuffles. And I don't know if you guys have looked at that, but I think there's something, my verification head and my kernel writing head or see like a connection here that I think would be useful.
Right, we haven't, but that's a great tip. Thank you.
Yeah, the layouts in general are complicated. I'm happy to talk about it afterwards, but I think it generalizes everything to like a layout as a pair of a shape and a stride that generalizes like bijective, or there's a bunch of conditions on them, but they have like co-operations, et cetera.
Right. So for now, our layouts are kind of basic in the way that they're just a bijection from ij into a position in an array. So we don't particularly model strides so far. And this means we don't allow you right now to take like a submatrix because then you need a stride. But we should definitely extend it to do this kind of thing. So yeah.
Right. The cool part is the copy operation then becomes generic. So I think you could write a generic pre-post condition, and then you could write an implementation ideally that doesn't have to mention very much because it's sort of discharged by the condition of the atom in quotes. So anyways, it's something we talk about. But
yeah, nice. Thanks.
Time for one more question. Anyone in the back, please?
Thanks for the talk. Could you speak a bit more about the GPU resource? Does it have a definition, and how do you use it in the verification? Because a lot of what you present can also be applied to parallel CPU programs, right?
Yes, so the GPU resource, you're right, it doesn't have a definition, it's more axiomatic. So we use it to control what you can spawn. So when you're writing CUDA-C, you cannot just put like triple brackets on any function. It has to be a global, it must have been marked with the global attribute to say that this is a kernel and you can spawn it. So the GPU resource is kind of what we use here to model this restriction, but it really is an opaque resource which is passed back and forth. So what we should probably really do is have a mode system in Pulse that allows you to say this function is GPU, and it's a different kind of function from others. But this resource thing kind of gets us most of the way there, but it doesn't have a definition. Yes, good catch.
Thanks. I have one question. I was not sure whether that while loop, if changed slightly, will give a problem. I haven't analyzed it fully. You had a while loop.
This one?
Yeah. Suppose we make the k thread ID x or something like that. Then that sort of means that each thread will do a different number of iterations because the shared comes in from outside. So would that will be a data-dependent loop? So I wasn't sure how.
So k is initialized as 0
I know,
there, right?
but
okay.
I'm looking at thinking of a different program where that k might be TIDX or something, thread ID. So you're comparing my thread ID with something that comes from above. So each thread will iterate a different number of times. Am I right? In that case, the amount of read-write accesses each thread performs is a data-dependent. Yeah, so I should work out, I don't know, yeah. So there could be, in general, data dependency is handled properly by permission-based separation logic, but I haven't thought through it. Do you have you run into any cases where that might cause an issue or not?
So not yet,
okay.
But I think most of these things, so for instance, we're not proving...
for every read you get, you don't take any permissions for every, you take a fractional permission and things like that.
Right, but it's not spent. So we don't do any kind of reasoning of like, every thread runs in the same constant time, or they use the same memory access. We don't do any of this right now.
Should be good.
But we could possibly do it, I think.
Yeah. Let's thank the speaker once again for a great presentation.
Thank you.
We have one talk by Jakub. Did I get the name right? Yes. Okay. And he'll be talking about, blanking. And microphone. Yeah. Something cool. Sorry, please state the name of your talk. Yeah. He'll be talking about structuring arrays with algebraic shapes. Jakub, this is yours. Okay. So this is Jakub presenting structured arrays with algebraic shapes. Please take it away when you're ready. Thanks.
Thank you. Like this. All right. Look good. Right. Thank you for coming to my talk. So my name is Jakub, and this is a paper co-authored with my supervisors, Dominik Orchard and Alan Mycroft, as part of my as a part of my thesis at Cambridge. And all right, let's get started. So as a quick introduction, static type systems are great, and we want more static type systems. You get guarantees, and you get essentially documentation of library interfaces you write, and the programmer can write better abstractions following types. But for array type systems, or for array languages, there isn't really sort of maybe a favorite typing discipline. And I would argue even that there's you end up with these two extremes where a lot of will be essentially untyped, or there will be very little type information, or people will immediately start going towards the extreme of having dependent types in their language. So, well, okay, so why might this happen? Why this polarization in this sort of area of array type systems? And I think this is to attribute to that there isn't quite enough nuance to what an array is, like as a value, and thus there's not enough to say about its type. Because a lot of libraries, like the ecosystem, sort of sticks to n-dimensional arrays in the style of Fortran, and maybe has 3 dimensions, has some specific element type, and then maybe there's 2 different ways where you can really write down what the syntax of array types is, where you might think of them as it's a scalar or a vector, which is another array, or it just has a specific rank. But what can you really keep track of is the element type, and then maybe the number of dimensions. And even the number of dimensions with some array primitives might end up being a bit crazy. And here, I think what you quickly converge to is you want to keep track of sizes of specific dimensions, because maybe operations that you're using depend on sizes matching, or you want to index and you want to know that your indices are always in bounds. So quickly, these non-trivial type systems will end up growing a dependency type, sort of carefully limited dependency type extension, like in Fulvark's case, or you have entire designs like DEX, where it's mostly about a dependent type system. But that's maybe, maybe not ideal. The part of the reason why you're getting these dependent types is size arithmetic. So you get primitives like, flattening arrays, like a matrix you want to turn into a vector. You want to concatenate a pair of vectors, and then you quickly get sums and products of sizes. And now you want these dependent types to keep track of these this arithmetic, and you get these expressions, and maybe you want a solver to figure out whether sizes are equal or if they are bounded or stuff like that. And this just adds this computational complexity and complexity for the programmer themselves, because the system becomes more complex, less predictable. So in practice, a lot of practitioners would just end up using untyped programming. You don't, if they're using Python with NumPy or PyTorch, they're trying to write down type annotations. They're really doing their best, but they don't end up doing a lot. And then maybe a lot of these research languages will have these dependent types, but maybe it's difficult to extend these in existing systems. And then even if you do put dependent types in your system, you still have these other sort of problems like existential sizes, or do you have jagged arrays in your system? Can you even write that down as a type, or is it just illegal? And maybe size polymorphism, where if you keeping track of sizes as sort of part of the type, then now this has a computational content, and this makes your system a bit more complex. So what can we do about this, and how can we address this? And I think what I sort of look towards is these generalizations of what array structures can be. So more than just n-dimensional arrays. And 2 particular sources of inspiration for me are labeled array axes, which come up in libraries this is from the Python ecosystem. One is called named tensors, sort of labeling dimensions of arrays, and another one is xarray. And another one is Napierian functors, which is this idea to generalize what an array as a container is. And this is explored by Jeremy Gibbons with array programming and applicative programming in the paper. And so where I go with this is to look, maybe look towards more functional roots, to like think about what works really well with functional languages, which is algebraic data types, and avoid dependent types, and then also look at more recent developments with type inference with subtyping. And we can sort of combine the two because we can get type inference for these sort of structural algebraic data types like records and variants, and we can sort of endow it with subtyping. And here I follow Stephen Dolan's algebraic subtyping, or sort of this sort of direction of this sort of seminal development. And the sort of key idea, the approach here, is to have structural record and variant types for shapes and indices of arrays. Or sort of vaguely like that. This is the vague idea. And then I equip it with subtyping and argue that this gives us interesting patterns, that this models interesting array programming patterns and stops you from making indexing errors in particular. All right, so the key ideas here. So introducing star. Star is this calculus that sort of develops these ideas formally. And it's a functional and pointful array calculus. Pointful here just ends up meaning that we focus on array comprehensions where we define the shape of an array, and then we say what is the element at each index. Like the elements of this array are given in terms of like a function of the index. And then arrays can obviously be indexed with an arbitrary expression, and they can be and their shape can be recovered with an operator. And as I've said, as I pointed, sort of shapes and indices are special. They're structured types. And besides the obvious, like you want arrays that can be indexed by integers because that's what arrays sort of are, you want to give them more, you want to make them, don't make them flat. You want to make them nuanced. And there are two pieces of nuance. There's product shapes and concatenation shapes. And these are respectively indexed by records and variants. And they're sort of denoted with these funny braces that sort of are similar to the corresponding standard notation for records and variants. So let's start off with looking at records. Like, why is it interesting to index your arrays with records? So for like a bunch of axis labels and existing shape types, we'll have a product shape, and this can be indexed by records of a corresponding record type. And here we'll say that this record can have more fields. So what this means, if I write down, for instance, like a series of RGB images with like 3 channels, I can write down the shape of an array which stores that. It's a 4-dimensional array. So if, normally I will just have a shape, a 4-dimensional array which is like 132, 32, 3 in shape. Here I can label these axes, and then I can index them with a record. And a fun thing I can do is that this record I index with can contain extra information. It can contain extra dimensions in the index. And for instance, here I added a dimension called depth, and it doesn't matter. This information can be ignored when I ignore. And this is used, how we sort of leverage subtyping in this system. And you can notice sort of special cases like if the array has no dimensions, it's a product with no dimensions, then it's in particular, it has exactly one element because you can index into it with an empty record. Now you've got variant indices as well, and these are also fun because if I think about, okay, I'll write down like a concatenation shape, so I write down a bunch of components, I'll say I have a left, center, and right component. Then the way you index with a variant type, so like a tagged value into an array of that sort of shape, this corresponds to selecting one of these components, like left or center, and they specify the index within the component. So maybe I index into center 4, so I index into the center component with the index 4. And again, there's like a nice special case, which is the array of shape with an empty concatenation shape. The concatenation that has no components is the empty array. So again, concatenations and variants are sort of connected in this way. Okay, so now you can make more complex structures out of this as well. So it's not just that I can make a product of like integers and there's a size sort of shapes and concatenation of size shapes, but you can have products of concatenations. So for instance, I can sort of refine the type I use for RGB, for RGB images. I can say that instead of saying that the channel dimension is of size 3, and then arbitrarily say that maybe channel 0 is R, and channel 1 is green, and channel 2 is blue, instead I can label these as part of a concatenation shape with appropriate sort of singleton cases, because like there's no more information within except which tag it is, whether it's red, green, or blue. And then I can index into this with something like row 15, column 17, channel green, right? So that gives me this nuance that before was missing, that before you have to keep in, knowing that, for instance, the size of a dimension is exactly 3 and the order between the different dimensions. Now it's sort of labeled and it has this extra structure to it. All right, so like here's a summary of sort of what this ends up developing to. So we've got sort of size shapes, product shapes, and concatenation shapes, and you've got some different examples. And what's sort of interesting to notice here is that product and concatenation shapes behave like records. Like up to typing, like you specify like what each dimension is, what each component is, and they essentially just behave like records. You can also project the individual components and dimensions. But what is special is that concatenation indices behave like variants. And this introduces like this funny complexity to the system where at some point you'll have to be able to sort of relate that, oh, I'm like trying to index into a variant, so I'm expecting a concatenation shape and not a product shape. And that's the general gist of it, of what types and values there are in star. But there's one more thing still to do, and that's one more key idea to star, and that's broadcasting. And rank polymorphism is great. It allows you to write more concise programs. And you might have this question of like, how can we generalize like rank polymorphism to this idea of structural shapes? And I think it works out quite well. And it still also corresponds to this idea of like having subtyping in the language. So when we have like NumPy style broadcasting, we'll have like funny things like if I have like three-dimensional arrays and certain sort of sizes are considered like certain axes are considered to be not present and can be repeated along that axis, then an analogous sort of phenomenon will apply to product shapes, and also one can be done for concatenation shapes. So what we'll say is that broadcasting of compatible shapes will yield its least common subshape, and subshape in the meaning of like what indices are contained in both shapes or like either of the shapes. So I'll give some examples of this to be concrete. So the first example will sort of show us that, okay, if I try to broadcast two shapes, which maybe are, again, used for like specifying images, so one only gives rows in a channel, another one only gives columns in a channel, and if I broadcast the two of these, then the common axis, which is channel, has to be sort of assumed to be equal in both of these shapes. This means that the shapes are compatible, but row and column are sort of propagated to the result because they only occur in one of these. In more general terms, what you can do with this is give like more point-free primitives for star. And these sort of rely on broadcasting. And I will say that, for instance, if I want to define an element-wise addition on like a pair of arrays with these structured shapes, then I will say that the shape of the resulting array will be the broadcasting of the shapes of the two original arrays, and then I will add things element-wise. I'll just like take X. And the reason this works out, the reason this makes sense is exactly because of subtyping. Because the broadcast shape will only give me like more specific sort of subtype indices, and this all sort of works out. Cool. So, where does star shine? Where do things go well? Like, what's an elegant example? So the example I like is padding. Because padding has always threw me off with sort of index arithmetic that rises and stuff like that. So we'll have a simple example. We're padding a matrix, and we have top, bottom, left, right cells. And we'll put +1s at top. I think I did it the other way around in the example, but don't mind that. That doesn't matter. Either way, we're padding a matrix. And the way you do it in like an imperative point-free setting, and really in any setting which has unstructured arrays, where the only thing I can really say is that the input is a two-dimensional array and the result is a two-dimensional array, is I have to set up the shape, and the shape is going to be a sum of a bunch of components, like a bunch of these individual sizes, and then I need to set all of the values, right? But the way I can only access the specific parts of the array that I want is I need to find the index ranges, right? And I feel like that's deeply unfortunate, because like these index ranges are sort of arbitrary. It's like you say that a certain thing has index 0, like for instance the top will have like, the top left element will have index 0, 0. And why is that the case? Why is that so different from bottom right? So obviously there's shortcuts possible in this code, but they're just shortcuts. Like the general principle of how this code has to be written is like this. It has to sort of recover those index ranges. Okay, so we're looking at star now, and we're going to sort of leverage the structure of the problem. And the structure of the problem is that we're producing a padded matrix that has columns and rows, which is sort of like a product. And now within those, we have like the different regions. We have like a top, center, and bottom region, and left, center, and right. This leads us to writing down this shape in star, which looks at the shape of the original array and uses that for setting the center parts, for the center components of the concatenations. And we have these two dimensions, row and columns, and within those we have, this exactly corresponds, like all of these possible cases of concatenations correspond to these 9 regions in the resulting array. And what's really nice now is we're using records and variants. We're playing with normal things, and we can do pattern matching by constructing an array of this shape, and then we can pattern match on what is in the row and column individually. And you can consider which cases we're in, right? Because if we're looking at the center, then we want to copy from the original array. And if we're looking at the top, then we don't care, we just return -1, right? And that's exactly where I think this all comes together. And this is a bit perhaps verbose, but the nice principle is that I think this is way more maintainable and way more obvious than writing down a bunch of index arithmetic and saying, oh, this range is from t to t plus l, and now guess whether that's right. Obviously no, because we're mixing t and l, but I feel like this is way clearer on like what information is actually being used. Okay. So I'll sketch the formal development of what comes up when we are like arising with star, because now you've seen that perhaps it is worth like developing this idea because of how products and concatenations naturally arise in like these very basic problems. So for operational semantics, it's like maybe a little non-obvious, but no, because I've said that we can index into arrays with sort of redundant information, there's this notion of like, what should an array store in terms of elements? And here like is a basic example where I store like these 3 different positions, and when I index with a position that with an index that has sort of more information to it, then I just ignore that information and find the corresponding entry that's actually stored in the array. For types, the types are also quite straightforward. There's a bunch of obvious things. The things in color are sort of more interesting. So we've got the record, variant, product, and concatenation types. And then we also got the array type. And I'm lying a little bit here, but for now, let's just sort of keep to the lie. But we sort of want to have an array type which says it has like a shape, and then it has an element type. And what's nice about this setup is that multi-dimensional arrays that are regular are given by product shapes. So if I really want jagged arrays in my system, then I can have just a nested array type which says I'm indexed by integers, and then within me are arrays also indexed by integers of some, with the array being of some size that's not unknown. So we don't need any existentials or anything fancy like that. But now I have to clear up the lie about sort of the array types. So there's a little bit of nuance when it comes to giving this subtyping. So as I said, for shapes and indices, they just behave like records and variants. So this is completely standard. It's like textbook subtyping. But for arrays, it's like a bit unobvious because you probably want your shape to like also behave under subtyping, and you would want it to be covariant or contravariant. But as you can find in the appendix of the paper, this isn't like something that works. It's because indexing is contravariant, but accessing shapes is sort of covariant in the shape. So there's a trick that we can use where essentially we keep track of like a bound, like an interval in which the actual shape type must lie. This is sigma 1 to sigma 2. And then when we give the subtyping rule for arrays, it sort of makes use of this fact. And then we separately use the contravariant part and the covariant part of this bound for indexing and shapes, which is shown exactly here on this slide with these 3 typing rules, which are just the most important typing rules in the entire calculus. They're just saying that as we construct arrays, we like propagate the appropriate shape and index types, and then when we index, we look at the corresponding bound, the one that sort of makes sure the system is actually sound. But there's this funny thing here in red, which is the iota function, or it's a meta function, which is it's a function on types. It sort of takes an existing shape, and it will get the index type which is compatible with it. It's a type of all index types that are compatible with that shape. So there's this funny bit here. And one more funny bit to mention is that broadcasting is a bit tricky. But what is like an interesting property is that in most cases, because it is in a way a subshape, we can just look at the subtype of the operand shapes. So that's kind of an elegant bit that again connects with subtyping. Okay. So we now have to look at iota though, which is how do shapes and indices match? How do we relate them in the type system? And this is done for this meta function, and it's got a really simple compositional definition. Essentially, we look at the shape type or the shape type, and we just replace all instances of the size things with the index things. So a product shape will be replaced by a record and so on. And maybe it's a bit weird to have this sort of construct in your type system. But it's actually like very reasonable. Like when we look at, like, for instance, Napierian functors, is the way they end up working out is they have this logarithm operation that says, if I have a container of this shape, what is the type of indices for this shape, right? And this is exactly what we're doing here. Analogously, there is an abstraction of containers independently type programming, and this one also uses something similar where we have a function on types, which given a type of shapes gives you a type of positions. Or a value of shapes gives you a type of positions. All right, so now with these things stated, because we know about typing and subtyping, we can say that star does actually have type safety. And the way you state that is just progress and preservation. But progress only holds up to integer indexing. Like at no point in the system did I ensure that integer indices always work out. What I can ensure is that there's a compatibility between sort of indices being structurally in bounds, that it's up to like those products and concatenations, but not necessarily up to integers. There's nothing in the system because that does sort of end up requiring dependent types. So, but I can end up, I can show that the typing, if I know that like shapes and indices match up to typing, that they match up to the structurally in bounds relation, and so indexing never fails. It only can fail at integers or sized shapes. And so where I can drag this further, and this is more conjectural, but seems to make sense, is that you can extend, so all of this was a star in a simply typed setting, and I believe you can extend star with parametric polymorphism and then design like a sensible type inference for it. And there is some, obviously this is something that will have to be worked out. I do have like a rough working implementation of this idea because it was part of a larger project on doing like sort of design of structural subtyping and type inference with structural subtyping. But here, for instance, one thing that we have to take care of is this addition of the iota sort of type meta function. It turns out it's a homomorphism in the algebra of types, in the lattice of types. And this gives us nice properties that allows us to sort of work with it in type inference. And so there's at the bottom there's an example of what sort of type inference might we want to do. But maybe an interesting thing to note here is why would you want to care about sort of shape polymorphism? Why would you want to have polymorphic type inference for star? And I think what's interesting here is that if you write functions in star that never sort of index the input arrays at integers, and obviously you can never index the input arrays out of bounds. Like you can only ever just ask the input array for its current shape and then like create an array over its current shape. But that just can't possibly lead to an index out of bounds because it only gives you indices in bounds if you're constructing an array of that given shape. In particular, they could all be structural. So either way, maybe that's not necessarily convincing, but I think it's definitely promising and it seems to work out in practice. Right, so I can start moving on to conclusions. So firstly, there's limitations to this system, and I've already hinted at this, that it seems algebraic subtyping and this approach of structural subtyping fits this very naturally, and it can be extended, but I can only test this with an implementation. So this is sort of a limitation of this work that has to be explored for the polymorphic case. Another case, I think something that people point out to me is that they find the notation quite daunting. There seems to be a lot of different braces and funny dots in the paper. This is all because there's like 3 different record types and also a variant type, because products and concatenations and records, they're all really just records. And there is this nuance to them that are obviously different. They have slightly different behavior in different places. But maybe it's like a bit funny that maybe the design should be flattened to just say that this is all like record types and one variant, like one record type and one variant type. There's also the integer sizes that, like, I think this is more symbolic. I think you could, like, have integers be usable both as a shape, as an index, but for technicality, this is how it's done in the development in the paper. There's also the question of could you embed this in like an existing language? Like it seems annoying to actually properly build like a new language based on just this specific one calculus. And I'm not exactly sure what the answer is here. I believe that with if you have like a proper implementation of row polymorphism in a language, and maybe I can't think of an obvious mainstream language that would support this, but I have this problem of wanting to switch between a record type and a variant type that has the same sort of fields in the way that it's done between concatenations and variants. So that's something to keep in mind. Maybe there's something to do with like if you could like have polymorphism or labels, but again, I think it's even less common for a language to have something like that. So implementation is also a very obvious example that arises. And how do you get performance in this implementation, in this sort of calculus that has so much like funny stuff going on in terms of indices and shapes, and how the data is stored in arrays? I think the idea for getting performance in star would end up being around erasing the subtyping, and this seems like a standard sort of procedure. If you want performance on anything that has to do with subtyping, you will need to erase subtyping to make sure that at every point you know exactly what is going to be the layout of the records that you're dealing with and what variant cases may arise. So this would end up being around monophasization. So it's likely that you couldn't like have amazing performant code generation for like fully like for like polymorphic star code, but with like knowledge of what the specific shapes are, it should be reasonable to generate static sort of layouts for the arrays. And there's like an example process of like what these layouts might look like, where like, for instance, I'll keep track of like for concatenation shapes, I'll like keep track of like at which index does that bit of the concatenation shape start, or that component. And lastly, and I think there's a lot of sort of future like sort of ideas to explore with star. I don't think it's just like this one silly idea where you just give give something like algebraic data types for arrays and funny stuff happens. Like go figure. I think there's like actually things to explore. And obviously one obvious thing is to look at polymorphism and what properly happens there. But also another funny thing I tend to notice when I would tell people about this is that they quickly start asking, oh great, you've got structured types, how do you get rid of them? And well, I think the answer here is to use some sort of coercion operator. So you can either try to keep it safe, you can say that this coercion operator has to work up to, sort of with respecting structure. But really, it's just an operator that corresponds to reshaping. If I've got reshaping in a classical sort of array programming system, I'll take an array of some shape and then I'll reinterpret that same buffer, that same data with a different layout. And this corresponds to a very similar operation, where over time I can get rid of pieces of structure and replace them. So that's like exploring what sort of operators should be used there, and this probably will have to be done in conjunction with looking at what performant code generation should even look like, and what sort of conversions are reasonable to do in, say, constant time without like extra overhead. And I think so, and in algebraic data types fashion, it would be interesting to look at recursive shape types. I think there's interesting sort of problems that this might be able to model. And lastly, I think there's some cases where maybe this is too naive. Maybe like, you know, sums and products, and the meaning that products and concatenations and records and variants are not sufficient for whatever you want to do. Like one obvious example that I came up with is stencils and convolutions. I think with something like filters, I think there's something reasonable you can do, that you can give it a reasonably shaped polymorphic signature. But for instance, stencil convolutions, I think you sort of quickly get deferred back to integer indexing. Like it's maybe not ideal. Maybe there's some more shape types and index types that you might want to be able to use. All right, but that brings me to the conclusions. So star is this pointful array calculus that has structured array shapes and indices, so they get equipped with structural subtyping. It's kind of like algebraic data types for arrays. That's sort of my inspiration. And there's this, I think, this potential for this work, for looking at type inference, for getting performance out of it, for maybe having it in an actual proper array language as an extension of its type system. And the way I look at its importance is that it's this middle ground in the design space of array type systems. Because you've got, you know, I think when you look at the polarization between a lot of the practical array type system, you know, array languages being basically untyped, whether they're embedded or otherwise, versus like, you know, the very safe but maybe a bit complex dependent types. And yeah, I think sort of lastly the argument sort of comes back to the case study, is that structured types will sort of lead you to better structured programs, because star isn't just about the types. It's about giving more structure to the values themselves, and hence sort of fixing the question, because perhaps the question that we're asking about like typing arrays is wrong. Like maybe you just can't type sizes that way. Maybe you should make the question different. You shouldn't type sizes as parts of shapes. You should make the shapes more interesting, so there's more interesting types to give them. And yeah, that would be it. That's the finishing thought. So thank you. I'm happy to take questions. Is there anyone ready? He's even got a mic.
Yeah. Very interesting. Very interesting.
Thank you.
I'm not really all current with arrays, but I'm very, very interested in Dolan's work on algebraic subtyping. So 2 questions there. First one is, you know, you spoke a bit about. I'm not sure whether you talked about the distributive lattice, but you did mention about broadcasting as basically a join operation, right? But you didn't actually mention it as a join of the distributive lattice. So conceivably there will be a meet as well. And does that have a name?
One more thing. So it actually ends up being, because it ends up being, I really hope I didn't make typos in the slide, but it ends up being a meet. And the meet, it is actually some messy things with algebra. That's the most messy thing about the system in terms of the algebraic subtyping bit. Because having it be a meet breaks the polarity restriction in Dolan's work in certain places. And so the prototype implementation that I wrote was using Perot's extensions to avoid this problem. They was using the Boolean algebra formulation of the type language. And then you can actually have a meet of types be a result of an operation, a result of broadcasting. As for the idea with joins, I'm afraid I do not know. I think I briefly thought about it, but I couldn't come up with a good answer. I assume it would come from like having like indices that belong in both shapes, and that would be the question of in what context do you want that.
It's a join, isn't it? I mean, or do you think of it as a meet instead? I thought, you know, for me, just looking at the definition, it's a join, not a meet. And so what you want is you have a join, you're looking for the meet, and not you have a meet and you're looking for the dual, that is the join.
Maybe we can chat about this later, sure. But I'm afraid I don't know at this moment.
It's a good
but
point.
Thank you for the question. I think there's like interesting things to explore with algebraic subtyping. So yeah. Hi.
How do you think you can model the rank operator, where you can choose to apply functions over different ranks of arrays?
Well, then the way you do it. So I think this is so suggested. Also, my slides are frozen. I don't know. Were they frozen for long? I hope not. Long.
Very long. From this slide onwards.
Sorry, why didn't anyone say? Because this is just frozen. Like it was progressing on my side. I was going for slides for the.
We know. Try unplugging and replugging.
I thought that you were. No, it's not. This doesn't help it. It's just frozen. The projector is frozen. No, I did have more slides. I was going for the other slides. No, it's still frozen. Yeah, I mean, I guess there's nothing to do at this point. It's very unfortunate.
I would say the intuitions that you expressed at the end were clear. So I was thinking you were extemporizing with whatever was here.
That's good to hear. It's unfortunate about the slides, but I think that was just the last few minutes, so it doesn't matter.
One more question, please. Yeah.
Yeah.
I have a question about the beginning of your talk.
Yeah.
Thank you. So my question is, so in the beginning I had the let's say the intuition that this is similar, what you propose, to positional parameter parsing versus named parameter parsing in functions.
Sorry,
how would you comment on that?
Could you repeat the question? I got distracted. Could you repeat the question?
Yes,
I think there's a relation. I think there's a lot of relation between just this general idea of like.
Shall I repeat my question or not?
Sorry, I think I did. But I think there's a general relationship between like having tuples in your language versus like having records and structural record types. Do you need to write down the type definitions, or do you use things unnamed? But sorry, could you make it more specific?
Yeah, that was my question. So in function calls or function parameter parsing, we have basically two approaches: the standard one, which is positional, and in some languages where you can alternatively or exclusively use name parameters.
Yeah,
and this looks a bit like the same. You give the axis a name, but my question would be, perhaps there's more, but that alone, how much does that help?
So I think that exactly corresponds to just labeled axes, right? Because when you just have function types which allow you to pass in keyword arguments, perhaps it more specifically corresponds to only having products and sort of tuple shapes, where they're sort of unnamed. Well, the difference here is that we also have concatenation shapes. So I think there isn't anything obvious that corresponds to that on that side. But yeah, that's exactly what I would associate it. I think that's a very good sort of way of thinking about in what cases might it be better to name your array axes as opposed to keeping them unnamed. It's exactly this difference between positional and keyword arguments, like in OCaml or something, or in Python.
Then what about naming the indices?
Sorry?
Instead of indexing by numbers, you could also indexing by names.
Within the array?
Yes.
That's exactly concatenation shapes. Well, like in some way, like if you recall if my slides work, then I would gladly show you. But if you recall the example with like specifying that an image has a channel dimension which is a concatenation of R, G, and B, then this is exactly, I'm just naming the three elements of the array, or like the possible indices. And I think that's quite convenient that I can just use names for like different parts of the array as a concatenation. But yeah, thank you for the question. Yeah, I think it's like there's definitely like a bigger language design question about how much naming should your user have, right? Because obviously you can't force your user to never name their variables, and you can say, oh, my program is so much more concise when I don't have any variables, but because I don't have any variable names in it. And some people will say that's better, but I would argue that you should give the user more sort of space for building richer abstractions and like having more structure in their code. Yeah.
The talk really came out well. I had a very quick comment or question. So view shapes, view changes in PyTorch. Would those kind of operations cause problems in this calculus? I mean, when you change the view, it can match in an unintended way. I was just guessing. Or
yes, so exactly. That's also something that would have really helped if I had slides, because there was an example there. It was exactly about this idea of coercions that. Yeah, I can show it to you in the.
We'll catch up. I think this
was
a fascinating area and very important. So thanks
thank you
for
very
the
much. Yeah, I'm very
presentation.
very glad that you enjoyed it. Thank you.
Okay, thank all the speakers of this session once again. And
thank you.
That concludes the array workshop. Let's give a big round of applause to the organizers for running such a nice workshop. I really, first time for me to attend. Thank you. Closing remarks?
Pardon?
Any closing remarks from the chair? Yeah.
Yeah, thanks very much. Is it on? Hello, hello. Yes. Yeah, thanks very much for coming here and joining, and for the stimulating discussions that we had. So thanks very much to all the speakers as well. And we are still looking for someone who's keen to be running the successor of this workshop, next year's PLDI. So anyone who's interested, please do get in touch. Thank you very much. Looking forward to seeing you next year.